Morning, Ellen.
Good morning, Jesse. I see we have two 22-minute talks to start the day, right? Yeah. Okay. I'm doing the timing this morning, so.
Okay, cool.
All right.
Is it strange being at Caltech?
It's a little strange, yeah. I see one or maybe two people a day, but it's hugely helpful because then I don't have to, tell my family not to run the microwave or do anything like that. So, yeah, it's good.
Right. Are you like walking in and out of the building with a disinfectant wipe just like on your hand?
You know what? I do have a little package of them, yes. Yep. I sure do.
When we drove across the country to get here to Ohio, we had to stay in 3 different hotels, and every night I would just make Phil and the kids stay in the car, and I just like went in and just like wiped down every single surface and tap and handle and button in the whole room.
Right, yeah.
And it was like, okay, go, roll in.
Now you can touch things. Are they having a surge in Ohio the way they are here? I think everywhere.
Yeah, I think so. Ohio reached a new record sometime in the last few days.
Jeez.
The Governor DeWine is making some kind of announcement today, probably about like more restrictions.
Right. Oh God. It's heartbreaking.
Yeah, my son asked one of his classmates to marry him yesterday. And this is actually not new behavior for him. Through daycare, he variously asked his male best friend, his female best friend, and all of his daycare teachers to marry him at one point or another.
Yeah.
But anyway, the mom emailed me last night to just be like, that was so funny. I nearly fell out of my chair. And I was like, oh yeah, like don't disappoint her, but this is like the 6th proposal he's made. But one thing I did say, I was like, it's nice to see them bonding even through Zoom, right? Like these kids have not gotten to actually play together. Just see each other on Zoom.
Yeah.
So I thought it was actually a nice sign that even with everything being remote, there's still some interpersonal connection.
Right. He feels a connection to someone. Yeah.
Yeah.
Yeah, I think kids do that a lot at that age because they see it as a way to always be with your best friend, like,
yeah.
Oh, I could just marry you and then you have to be with me all the time.
Right, exactly. Makes me feel like hopefully that means Phil and I are like modeling happy marriage.
Yes.
But Hugo's just like, okay, this is the state. This is what I need to achieve.
Right. Oh, that's sweet.
I could just be projecting.
That's okay. That's what you do as parents.
We have today's e-zine almost ready, but one of the authors hasn't signed the Creative Commons license, so I just gotta wait for that.
Okay.
I'm gonna try it from my own email again, but this time I'm gonna break it up into 2 emails, 2 blocks of emails, 300 to one, 300 to another.
I really think you can use Mabel, but I know.
Megan asked me not to. I'd rather not. Maybe by Friday we'll have worked out how to email 600 people a PDF.
Right. Megan and I talked about it yesterday, and she thinks it's fine. So, anyway, you do what you want, but I think it's okay.
Do I look yellow to anyone else? Good morning, by the way.
Hi, Lauren.
Morning.
I mean, a little bit.
Oh dear. This is my office lighting. I came for the internet connection, but I seem to have gotten an inadvertent filter change thanks to our fluorescent lights.
It's not. I mean, if you hadn't said anything, I'd have just been like, "Oh, she's somewhere with lighting." So I
Yeah.
think it's fine.
Okay.
You don't. It's not like Oompa Loompa yellow. Like it really does look like you just have a yellow light.
Okay, thanks.
You do have some amount of time if you want to go find a lamp or something if it's going to distract you.
Shoot, I have a bulb for my transit demo, but I don't actually have the lamp base. Damn it.
Just for your whole talk, just hold it in front of your face.
Oh God, yeah. Well, I don't even have like anything to plug it into. It's just like the bare like bulb.
Oh, I see. It's literally just a bulb. That's not going to work.
But yeah, maybe I can like urge the sun to come up here so that I have some natural lighting.
Oh, I'm sorry. What time is it there?
5:42.
Oof. Sorry.
It's okay. I'm happy to be here.
Stupid round planet. Hey, Louise, I don't have any announcements to start off. So when we get to the top of the hour, feel free to just kick it away. At the end of the session, I'll like say something about the break.
Okay, I'll make sure to pass it back to you.
Thanks so much. I'm gonna go.
Is it okay if I post a little announcement in the chat right before we start, kind of with the the usual rules?
Yep, that's perfect. Thanks.
Great.
Helen?
Yes.
Okay, that's all. I just really wanted to make sure you are hearing me.
Yes, I hear you. Yep.
Very good. Thank you. Morning, Jesse.
Hello. Okay, I'm back with a cup of tea, so ready to start when everybody's ready.
Yep, I got my cup of tea also.
Can you hear me well?
Yes, that was nice and clear.
Yeah, it goes well.
Okay, thank you.
All right, I think we're close to getting started. Jesse or Ellen, I see there's, okay, no, someone already asked it. There's a question in the Q&A, but I'm just gonna mark it as answered so we can get started. All right. It's nice to see a bunch of people have logged on already. So hello and welcome to the session today on system architectures from the point of view of an observer. We have 5 very exciting talks, and we also have a bunch of posters you guys should make sure to check out that will be covering this topic. So just to remind everybody to please use the Q&A feature to ask questions, and I very much encourage everybody to also post questions during the talk so other people can upvote your question in case they're also interested in it. And if you're interested, you can post your question anonymously as well. So I should remind everybody that this meeting is recorded. Yeah, so the first talk of today, my name is Louise Nielsen and I'm a PhD student at Geneva Observatory, and I'll be the chair for today's session. So our first talk will be about what we can learn about multi-planet systems by Wei Su from the Canadian Institute for Theoretical Astrophysics. So Wei, when you're ready, you can unmute yourself, and we see your screen already.
Okay, I hope you can see my screen and hear me clearly. So, do I see the timer? Oh yeah, here it is. All right, yeah. Thanks everyone, and thanks for the organizers for organizing this very good conference in this difficult time. So, as mentioned, I'm currently at the Canadian Institute for Theoretical Astrophysics as a senior research associate, but in a few months, I'll start a faculty job in Tsinghua University in Beijing, China. So let me take the chance here to introduce very briefly what we do in Tsinghua University. So the astronomy department at Tsinghua is very new. It was established early last year. And that said, we have a very strong exoplanet team at Tsinghua University. So here I listed all the faculties working in the field of exoplanet and planet formation, including Xinyin Bai, doing very nice work about microphysics in protoplanetary disk, and Chris O'Mell working on planet formation and in particular pebble accretion, and Su Mao, who is also the chair of the department, is a pioneer in the field of gravitational microlensing, and Sharon Wang, who spoke, I think yesterday, about her work on RV observations, RV follow-ups of exoplanets. So me and myself works on exoplanet statistic architecture and gravitational microlensing. So exoplanet is focus, one of the three selected fields that we want to focus, the other two being high energy astrophysics, cosmology, and galaxy formation. So if you are in the job market, please pay attention to, please find out our job ads in AAS job register. We are hiring at both faculty and postdoc levels. So please check out our website as I shown here. And if you have any questions, please get in contact with me. So, okay, so back to the science. So we heard, so we take our solar system as an example to just as a start to say what we learned from multi-planet systems. Okay, so our solar system planets have very diverse properties with separation spanning roughly 2 orders of magnitude and the mass spanning roughly 4 orders of magnitude, as shown in the lower left plot here. So solar system planets have small but substantial orbital eccentricities and mutual inclinations. So the plot, so the figure shown on the right is the relative inclination of all other solar system planets to our Earth orbital plane. But if you define the mutual inclination as the inclination relative to the invariable plane of the system, which is roughly controlled by the Jupiter's orbital plane, then the mutual inclination is typically within 6 degrees. And also we know from different pieces of evidence that our solar system was once very dynamically active, and according to studies of the long-term stability of solar system, it may have a chance to become chaotic again in giga-year timescale. So there are other things we know about solar system, but let's just focus on these 3 pieces of evidence. Now let's put solar system into the context of extrasolar system or extrasolar planets. Now this figure we've seen many times that shows the planets from different techniques versus the solar system planets. Now, if we turn off the difference from different techniques, but turn on the difference depending on whether they are in known multi-planet systems or not. So this is what we would get. So you can see the red dots are planets found in systems with known planetary companions. So multi-planet systems are everywhere on this plot. So of course, we should know that even if a planet is not known to have planetary companions, that does not necessarily mean they don't have companions, because it may just be a detection, selection bias or detection bias. Now, the first question we want to ask is, are all multi-planet systems flat or coplanar? Now, from transit methods, using Kepler data, the one technique to probe to answer this question is the so-called weighted transit duration method. And I think on Monday or previous talks have briefly mentioned about this technique. So essentially, you have a pair of transiting planets, and the transit chart length between the inner and outer planets can be used to probe the mutual inclination. So it is given by essentially the impact parameter between the inner and outer, and this impact parameter, the ratio between these impact parameters are related to the major axis, and therefore the ratio of the period. Now, observationally, you can show that this is essentially the transit duration scaled by the circular velocity, which goes as the period to the -1/3 power. Now, using this technique, people have shown that the mutual inclination dispersion between transiting planet pairs in Kepler data is typically small, around a few degrees. Here I quote 3 degrees. However, we should also say that this is more like a lower limit, because this technique does not does not work for all cases. For example, you can only do this thing for transiting planet pairs. If another planet is not transiting, you cannot apply this technique. And we know transiting planet pairs preferentially have small mutual inclinations. That's the first thing. The second thing is that if since this parameter does not care about the sign or the relative orientation along perpendicular to a line of sight, then you can see it only gives you the absolute value between the mutual inclination along your line of sight. To take an extreme case, if these two planets are on the same plane but are counter-rotating, then that means the mutual inclination is 180 degrees, but you won't be able to tell from a co-rotating and a coplanar system. So therefore, we should take this a few degrees more like a lower limit. Now, another issue with the coplanarity or near coplanarity of multi-planet system is that the Kepler planet, you would have this so-called Kepler dichotomy. Now, this was introduced also briefly in previous talks, just to a very brief recap. So I take this figure from Blood and Johnson work to demonstrate the point. So you have the histogram showing the number of systems with a given number of transiting planets. Now, if you assume all the multiple systems have the same kind of mutual inclination distribution, and you can reproduce all these high multiples, but you under-predict the first data point by more than 50%. That means you need at least a different type of planetary system to explain the transient multiplicity distribution. So this is the Kepler dichotomy. Now, of course, people will say that this might just be a failure of the very simplified model, but then fundamentally, I think that also means the transient method cannot constrain the mutual inclination very well, because the mutual inclination is strongly degenerated with the intrinsic multiplicity, namely the number of planets in the system. Now, this plot is an example to demonstrate the point. You can see you have a very strong degeneracy between the number of planets per star and the scatter in the mutual inclination. So therefore, if you want to constrain the mutual inclination based on transit method alone, then you need to make assumptions about the intrinsic multiplicity distribution. Alternatively, you can combine with other techniques such as radial velocity, but in this case, because transit method and radial velocity have very different selection biases, then you have to make a lot of assumptions in order to for this to work. Alternatively, you could combine transit with TTV, because TTV and transit are drawn from the same planet sample. Now, in this case, you should take TTV as a detection method rather than a technique to characterize the known transient planet. Now, the mutual inclination, we said here, a key assumption is that the mutual inclination is fixed for different multiplicities, but in fact, the mutual inclination depends on multiplicity, namely the number of planets in the system. Okay, let's see. So the histogram, the cumulative distribution shown here, as was also shown in Eric Ford's talk, shows the distribution of this Cosside parameter for different transit multiples. Now you can see once you increase, you have more and more transit planets in the system, then this distribution, the Cosside distribution, has a more steep rise at unity. That means you have a smaller mutual inclination. So therefore, there is observational evidence and together with the theoretical arguments suggesting that systems with more planets should have smaller mutual inclinations and are dynamically colder. Okay, so that's the mutual inclination part. Now on the eccentricity part, now you can also use the normalized transit duration to probe statistically the eccentricity distribution of Kepler planets. Now here the T0 is the transit duration you would get if you have a circular edge on orbit. So it depends on the mean density of the star. Now with both astroseismology and spectroscopic surveys of Kepler stars, people have shown that transit singles have a relatively large mutual inclination eccentricity dispersion at 0.3, whereas the transit multis have an eccentricity dispersion around 0.05 or a few percent. Now, in fact, if you again plot the cumulative distribution of this normalized transit duration ratio, you can see the difference goes further than just single versus multi. So here you can see with an increasing number of planets in the system, this cumulative distribution again has a steeper rise at unity. That means you have a smaller orbital eccentricity distribution. So again, orbital eccentricity, systems with more planets also have smaller eccentricity. So RV planets also seem to have a similar behavior, although there are a lot of strong selection biases that we need to be caution about. So this leads to the so-called intrinsic architecture of Kepler systems. Okay, so this plot shows the eccentricity dispersion and inclination distribution dispersion on the y-axis, and then the x-axis means the number of Kepler planets. Now here, let's just focus on the 1 point by 1 point. So the first point is this back square. That means that shows the transit singles having mutual eccentricity dispersion around 0.3. Okay, and the second point is this mutual inclination dispersion about compact systems from Kepler. Here I use 5-planet systems as example. So these systems have relatively small mutual inclination, less than 1 degree. Now, based on statistical modeling of including transit and TTV statistics, one can show that the dispersions in both eccentricity and inclination can be scaled as a power law of the intrinsic multiplicity, and it's a steep power law with power law index between -0.2 to -0.4, although a different work by He et al. Shows a slightly different but qualitatively consistent behavior. So what we learn from this is that, again, fewer planet systems are dynamically colder, and also each system has on average 3 planets. And our solar system fits well in this picture, but that might just be a coincidence. Okay. The most important thing would be this: it seems to suggest that dynamic evolution may have reshaped the system architecture to a large degree. Okay, so the mutual inclination affects our determination of the frequency of planetary systems. Now, the simple way to say this would be, so if you have a survey with a number of detected systems, in order to get the number of intrinsic planetary systems, you need to correct for the detectability of a typical planetary system. Now, if you assume planets are coplanar around the same system, then you have a very narrow inclination window where you can see the system. Therefore, previous results assuming coplanarity said that more than 50% of sun-like stars have Kepler-like planets. Now, if you introduce relatively large mutual inclinations, that means the detectability is higher, and therefore the intrinsic frequency of planetary systems is smaller. So therefore, in our work, we found that the fraction of sun-like stars with Kepler-like planets, by which we mean planets in this red region, is around 30%. Now, of course, this is a very irregular parameter space. Now, if you want to extend it to larger regions, maybe the fraction of stars with planets would increase, or maybe not, if the planet occurrences are strongly correlated. Hopefully, I'll have the time to say a little bit more about this later in this talk. Now, I want to skip the discussion about the spacing, but I want to say that even though Kepler systems are dynamically packed, there are still plenty of room to have planets interior or exterior to the known planet. Now, I feel it's probably necessary to very briefly talk about the intra-system variation. So I think there will be the focus of the next talk. Now, observationally, people found the Kepler multi-planet systems tend to have very similar size and mass. but this, whether or not this is just selection bias or astrophysical, is under debate. Now, I don't want to go to the details, the technical details, but just want to use our solar system as an example. So again, our solar system has very diverse properties, both in particular in mass and radii. Now, in Kepler's eye, this is Kepler's sensitivity region. If Kepler had a chance to detect solar system, most likely you would see Venus and Earth, and these two planets have very similar mass and very similar radii. So, but this kind of similarity is not representative among solar system planets. Now, Kepler planets have some similarities to solar system, but they are very heavy. So within 1 AU, we said there are 3 super Earths, each with a few Earth mass. Let's say 5. So in total, within 1 AU, you have in total 15 Earth mass solid material. That's roughly almost an order of magnitude higher than what solar system has within 1 AU. And then again, our solar system have outer giant companions. So do Kepler systems also have outer giant companions? Well, indeed they have, based on statistical studies of super Earths, which we define by planets in this region. The super Earths preferentially have cold Jupiter companions. It's statistically higher than what you would expect if you don't know there is a planet or not. So that's the fraction of stars with cold Jupiters, which is 10%. There's also a metallicity dependence. Now, what's more interesting is that if you invert this conditional probability, you will find once you have a cold Jupiter, the chance to have super Earth is nearly 100%. Okay, this value is probably too high to be reliable, but there are independent confirmations from the very valuable long period transiting planets from Kepler. So different studies have looked for the long period transiting planets in the Kepler data, and they found a large fraction of them are associated with inner small transiting planets. So this high fraction of cold transiting long period transiting planets with inner small transiting planets can only be explained if there is a very strong inner and outer correlation. Okay, so that's the statistical confirmation. Also, of the individual systems, in particular, in non-Arvis cold Jupiter systems, TESS has been finding more and more transiting super Earths, and in the future, TESS plus Gaia will have some. Will provide maybe hundreds of systems with both inner small and outer giant planets. Okay, so theoretically, this strong.
Yeah. Wait, if you want time for questions, we should start wrapping it up. We only have 2 minutes left.
I thought it's 4 minutes for. Okay, anyway, I'll be quick. So this inner-outer correlation challenges the formation of Kepler planets, because migration models typically expect an anti or no correlation. Now on the Poisson process, I'm not gonna just skip that. And then, okay, just to very briefly summarize. So dynamically, from what we have learned from multi-planet system, first, dynamic evolution may have reshaped the system architecture largely. Second, planet formation is a global thing. Whether or not you have planet at one region, have some dependence on the existence of planet in a different region. And looking forward, it would be good to find multi-planet systems around young stars, and also we might need to combine different detection techniques to have a global view of planetary system, because different techniques only probe a different region in the planetary space. So with that, I'll just stop and take questions. Thanks.
All right, excellent. Thank you very much for a very nice talk. All right, so we have time for 1 or 2 questions. The first one posted in the Q&A is about selection bias. So there are a lot of pockets of parameter space where planets seem to not exist either at high eccentricities or small periods, for example. When is this when is this an effect of selection bias, and when is it not?
I guess you mean the selection bias in the Kepler intrinsic architecture study. Well,
yeah, I presume so.
So we took into account the transit probability, but not the detection bias in the pipeline. That's why we define Kepler planets as planets roughly in this region. So this underlying contour is the detection efficiency of the pipeline. So we take roughly median efficiency as the region to define what we mean by Kepler planets. So in that sense, yes, we did not take into account the detection bias in the pipeline, but we define our planets based on the sensitivity of the pipeline.
All right. Sorry, we have a lot of other questions ticking in. So we have one that's quite interesting. So comparing what you've just presented to our own solar system, doesn't our solar system violate the correlation between cold Jupiters and super Earths?
Yeah, that's a very good question. I didn't have the time to talk about it. So on one hand, yes, one can say that we have cold Jupiters but no super Earths, so that put our solar system in a very rare category of planetary systems. But on the other hand, it seems like systems with inner small planets and outer giant planets are a popular kind. So generally speaking, our solar system like architecture is a popular type. So I think it to some extent depends on how you define a solar system like planetary system. You would have a different answer to this question. And also there are proposals suggesting maybe there have been some super Earths in the very early days of our solar system, and then they got disappeared in some way for some reason.
Mm-hmm. All right, thank you very much. So our next speaker is Lauren Weiss from the University of Hawaii in Manoa. And she will be speaking about demographics of multi-planet systems. So I should say that we have a lot of unanswered questions from Weiss' talk, so those will be transferred to the Slack channel, so feel free to follow the questions over there. So Lauren, when you are ready to share your screen, excellent, and unmute yourself, the floor is yours.
Can you hear me?
Loud and clear.
Fantastic. Aloha, thank you for inviting me to review this talk. Multi-planet systems are natural laboratories in which planets formed around the same star and within the same protoplanetary disk, offering a controlled environment for studying planet formation. This talk is about the planet orbits, sizes, and compositions in multi-planet systems, and about how planets are related to their planetary siblings in each of these properties. The number of detected multi-planet systems is sufficient to do statistics. There are 735 multi-planet systems, including nearly 2,000 planets, 1,400 of which are transiting. 76% of the transiting planets are smaller than Neptune, and 88% of them orbit with periods of less than 100 days. The wealth of multi-planet systems allows us to pose the following questions. What are the patterns in planetary system architectures? And what can those patterns teach us about planet formation? As part of the California Kepler survey, my teammates and I measured the properties of 909 transiting planets in 355 multi-planet systems. The planet orbital periods and transit depths come from Kepler. We used the WM Keck Observatory to obtain 1,300 high-resolution spectra of their host stars, which allowed us to determine precise stellar properties and planet radii in hundreds of multi-planet systems, including 51 CKS systems that have 4 or more transiting planets. In this plot, each dot corresponds to one planet, with each row being a planetary system. The rows are ranked by stellar mass with high mass stars at the top. The planet's semi-major axes are logarithmically spaced on the x-axis, and the sizes of the planets are to scale, with the planets colored by their equilibrium temperature. Let's zoom in to get a closer look. I also recommend that you use full screen mode to view this part of the presentation. Here's a zoomed in view. We will take a very brief and safe flight over these 51 planetary systems so you can see them in detail. During your flight, be on the lookout for any patterns. I hope you've enjoyed your Peas in a Pod Express flight. What I see is that planets in the same system often have similar sizes and regular orbital spacing. I have highlighted some examples in pink boxes. We call this the Peas in a Pod pattern. We can see by eye that planets in the same system often have similar sizes. But how can we quantify this pattern? We took pairs of adjacent planets in the same system and compared the size of the inner planet on the x-axis to the outer planet, which is on the y-axis, for each adjacent pair. The sizes of the adjacent planets in the same system are significantly correlated. How can we quantify the regular spacing? We do something very similar. We took all of the systems that have 3 or more transiting planets and compared the ratio of orbital periods for the inner pair of the triple on the x-axis to the outer pair of the triple on the y-axis, iterating through all the triples. And again, we find a significant correlation. One last pattern is that the planets with the greatest separations are larger than the planets with the closest separations. How can we quantify this pattern? For each pair of planets, we plotted their period ratio on the x-axis and the average size in the pair on the y-axis. There is significant structure to this plot, with the smallest planets tending to have the closest orbital spacings. I will mention quickly that the planets that are less than 1 Earth radius actually have mutual Hill radii that are about 20 dynamical units, as opposed to the other planets. So if you're thinking mutual Hill spacing is the structure that's going on here, I don't think that's right. And I think this plot needs more investigation. Shortly after I first presented the Peas in a Pod pattern, Milholland et al. Found that in 37 Kepler systems with transit timing variations, the planets have similar radii and masses to their neighbors. This plot is showing the planet mass versus radius. Each dot represents a planet, and the colored lines connect planets to their neighbors. The on-the-graph distances between the planets and their neighbors are shorter than if the masses and radii were drawn at random. Although planets are similar in size, they are usually not the exact same size. Chiardi et al. Found that the outer planet is larger in 60% of pairs. And also, although the planet spacing is regular, Fabrici et al. Found that the Kepler multis are not preferentially in mean motion resonances. Let's briefly review these many patterns I've just described. Planets orbiting a given star are similar in size and mass. Planets orbiting a given star also have regular spacing, and there is a relationship between the characteristic size of the planets and their spacing. The outer planet of a pair tends to be larger, and planets are rarely in mean motion resonances. So, what can these patterns teach us about planet formation? Gilbert and Fabrici noted that the planetary spacing is so regular that we can predict the presence of planets in the gaps, I have highlighted some examples to illustrate peas in a pod that appear to have a single missing planet. In Kepler 20, a missing planet was indeed discovered in the gap. The systems with gaps can be identified by their high gap complexity, a term that Gilbert and Fabrici used to quantify the irregularity of the orbital spacing. So these systems have high gap complexity, but are otherwise fairly typical peas in a pod. Adams et al. Developed an energy optimization framework that describes both the peas in a pod and runaway growth. They optimized the energy of the system, including the planet's self-gravity, and found two solutions for how the mass is distributed between the planets. Below a critical mass, the energy is optimized when the planets are similar in mass and regularly spaced, like peas in a pod. However, above this critical mass, the energy of the system is optimized when one of the planets undergoes runaway growth and dominates the mass budget among the planets. The critical mass for runaway growth is correlated with the planet spacing. The closest together planets must be small, whereas the more widely spaced planets can grow more massive before runaway growth occurs. If the closely packed planets grow too large, the system becomes unstable, which is perhaps why we don't have examples of these systems. However, the systems with sufficiently wide orbital spacing survive even when one of their planets dominates the mass budget of the system. Examples include KOI 94 and WASP 47. The energy optimization scheme predicts that the peas in a pod pattern should break down at 1 AU, if not interior to that distance, where the critical mass for runaway growth drops to about an Earth mass. Even the most dust-poor systems probably have enough material to form an Earth mass planet at 1 AU, which would then undergo runaway growth. McDonald et al. Have demonstrated that peas in a pod can grow in situ. On the left are the CKS planets, ranked by my estimate of the total solid mass among the detected planets. On the right are the in situ simulations by McDonald et al., which are ranked by the solid surface density of the disk. Let's take a moment to admire the similarity between the observations and the theory. Here is another example of a group of planets that are thought to have grown in situ. Do the terrestrial planets, which are shown to scale, remind us of the peas in a pod? My first observation is that none of them are sub-Neptunes. They are all Earth-sized and smaller. Earth and Venus have nearly identical size, mass, and interior compositions. However, their neighbors Mercury and Mars are much smaller, with Mercury having less than half the radius of Earth and approximately 1/20th of Earth's mass. Although Mars has a similar interior composition to Earth and Venus, Mercury is comparatively iron-rich. Earth also has a large moon. Mercury and Earth's moon motivate what we call the theory of giant impacts, a narrative in which rocky protoplanets collided in the young solar system, stripping away Mercury's silicate mantle and violently assembling Earth's moon. But is the composition diversity of the terrestrial planets unusual? We can express the compositions of the solar system planets on the density radius diagram. Earth, Venus, Mars, and the moon form a line in which planet density increases with increasing planet size in a manner consistent with the compression of rock. These bodies all have Earth-like compositions with roughly 30% of their mass in an iron core and about 70% of their mass in a silicate mantle. On this diagram, you can see that some exoplanets have similar compositions. However, the majority of exoplanets that are larger than about 1.5 Earth radii have densities that decrease with increasing radius, a pattern that is indicative of substantial volatile envelopes. Note that the iron-rich planet Mercury is different from the other terrestrial planets. How often do multi-planet systems have composition diversity comparable to that of our terrestrial planets? To answer this question, I am leading the first radial velocity survey of the composition diversity in multi-planet systems. This survey is a NASA Key Strategic Mission Support Program that is fulfilling the Kepler mission's legacy to understand the compositions and architectures of systems with small planets. The project receives equal support from the University of Hawaii. My colleagues and I are measuring radial velocities at the W.M. Keck Observatory for the systems shown at the left. On the left plot, each point corresponds to one planet, and its position on the x-axis corresponds to the orbital distance of the planet, with a size corresponding to the planet radii. Each system orbits a bright star with V magnitude less than 12.9 and has at least 2 planets for which we think we will be able to constrain the planet composition. Our survey builds on several systems for which planets have already been measured and will triple the number of Kepler systems in which 2 or more planets have densities that are characterized by radial velocities. We are currently 75% of the way through our survey, but now let's look at some preliminary results. This is a system where the planets are like peas in a pod, similar in size and regularly spaced. Our preliminary analysis finds similar compositions for the planets as well, with all 3 planets positioned on the branch of the density radius diagram that is consistent with volatile envelopes. Here's another system where the planets are similarly sized but smaller. At 1.5 Earth radii, these planets are near the transition between rocky and gas-rich planets. Both planets have high densities that are consistent with rocky compositions. However, not all planets of about 1.5 Earth radii are necessarily rocky. This system has 2 planets that straddle the radius gap, but they straddle it backwards, with the larger planet closer to the star. Owen and Campos Estrada have demonstrated that in systems that straddle the gap backwards, the inner planet must be substantially more massive than the outer planet in order to hold onto its atmosphere, despite the more intense radiation it receives. Thus, this system is especially useful for testing atmospheric mass loss models. Since the y-axis of this plot is density, I have printed the planet masses on the plot for clarity. We find a higher mass for the larger inner planet than for the smaller outer planet, consistent with a system that has survived photoevaporation, although other formation models are not ruled out. In our own terrestrial planets, the composition diversity is attributed to an era of giant impacts. Do other multi-planet systems have evidence of giant impacts? This system has 2 planets that are both 1.5 Earth radii, but they have a larger planet in between them. And in fact, it's large enough that it must have a volatile envelope. We are tentatively measuring a difference in density for the 1.5 Earth radius planets, with the inner planet having a high density that is consistent with a history of collisional stripping. This system reminds me of our own terrestrial planets, particularly the composition differences between the high density inner planet Mercury and the moderate density outer planet Mars. These 4 systems reveal the composition diversity of multi-planet systems. The apparent peas in a pod systems do have planets with similar masses and bulk densities. However, in systems that have size diversity, the planet masses do differ, even in an example that has some similar planet sizes. I am eager to finish this survey in the fall of 2021. In the future, extreme precision radial velocity machines like the Keck Planet Finder will enable mass measurements for hundreds of planets in multi-planet systems. KPF will have intrinsic radial velocity errors that are an order of magnitude smaller than those of high-res. The improved stability and throughput will allow us to push our studies of low-mass planets to stars with V magnitudes brighter than 15, including iconic systems like Kepler-11. In order to continue rapid progress in exoplanet demographics, we need another space mission dedicated to the task. The ESA-Plato mission might do that because prioritizing the occurrence of Earth-like planets in the habitable zones of Sun-like stars requires a long stare. And this design is equally amenable to extending our knowledge of the peas in a pod pattern. We would be able to ask, how far out does the peas in a pod pattern go? And better investigate, what is the relationship between peas in a pod and giant planets? However, the stare strategy of Plato has not been finalized. So if you are on the Plato mission or have a friend who is, I hope that you advocate for a long stare strategy.
Are you getting ready for questions, Lauren? Oh, great.
We're out of time. So here are my conclusions and I will take questions. Thank you. Mahalo.
Excellent. Thank you very much. That was a lovely flight over the KOI systems. So we have a lot of very interesting questions for you. Let me just quickly see which one we'll go with first. So the first one is from Ilaria Pasquiti. Sorry for saying that wrong. Thanks for a very interesting and clear talk. You mentioned that peas in a pod pattern can be reproduced by in situ formation. Can it say anything about pebble accretion to exclude it or confirm it, perhaps?
That's a great question. So I have talked with some of the pebble accretion theorists, and they assure me that they think they can make peas in a pod with pebble accretion, but I have yet to see a plot from their simulations that looks like the McDonald et al. Plot. So I'm hoping that they will generate some plots that make it easy for me to understand whether or not they are reproducing these patterns.
Right. And we'll do one more question. So this is about selection biases or observation bias. So both Dave Bennett and Elliot Freimuth asked the same question. If you've considered contribution of selection effects to the patterns, for instance, small planets are easier to detect in short period orbits and so on. And then as a follow-up to that, what kind of follow-up observations could we use to break that that observation bias?
Okay, so that's a great question. To test the role of observational bias, we conducted a very simple null hypothesis test. For each system, we used the observed stellar properties in planet orbits, but drew the sizes of the planets at random, trying multiple size distributions from which we drew the planets at random. Our draw for each planet size did not depend in any way on the sizes of the other planets in the system. So this was a test of the null hypothesis, which is that planets in the same system have uncorrelated radii. And to mimic the Kepler detection bias, we required that all the planets in each system were actually detectable. I want to point out this is a controlled experiment where we've only changed one thing at a time. The only thing we changed was the planet radii in each of the systems. So this is different from the full forward models where someone proposes an underlying architecture and then forward models what it would look like to Kepler, right? We are only changing one parameter at a time here. So it's a very different kind of test, but it gives insight about what random planet radii would look like. And the result is that with these random planet radii shown at the left, we cannot reproduce the observed planet radii. As for giant planets, that's tough, right? Because the transit probability diminishes with the orbital separation of the planet. However, radial velocities are an excellent tool for discovering giant planets. And I actually have a long-standing program where I've been looking for giant planets around a few Kepler systems, but most of them are actually not really peas in a pod like. We can only sort of skim the brightest systems, but with KPF, we will actually be able to do this experiment for the fainter systems to test whether these fainter systems that have the peas in a pod architecture tend to have giant planets, yes or no.
That's really exciting. Thank you very much. We'll give you a quick applause here and move straight on to the next talk, which will be by Jack Lissauer from NASA Ames. Jack will be speaking about architecture and dynamics of Kepler multiplanet systems. So whenever you are able to share your slides and unmute yourself, Jack, the floor is yours.
Okay, can you see my slides?
Yeah, it looks very narrow though.
It's very narrow. Okay. And I will switch this. Okay.
Perfect.
Does that
Thank
look
you.
better?
Perfect.
Very good. So I am going to be talking about something closely related to the title I originally gave, but things changed a little bit. So I'm going to be looking at some architecture aspects, in particular 3-body resonances, and how that is related to perturbations, TTVs, and their implications regarding the ephemerides of Kepler planets being not quite as reliable as the formal errors suggest. The motivation for this study was indeed an architecture's study. It was looking at how common 3-body resonances are among Kepler planets. And I'll discuss some of the things that we found that really surprised us and the implications that had for the orbital periods that we were using. So we investigated further the orbital periods, and I'll discuss the comparison of the orbital periods that are given in KOI catalogs, including and especially the one that Jason Rowe mentioned on Monday that is in progress. I'm going to compare those to some other estimates of orbital periods of the same planets that Holzer et al. Derived for almost 200 planets by doing sinusoidal fits to observe transit timing variations. And then to some of the dynamically solved systems where we have done detailed dynamical models and propagated these into the future. And then I'll give you a little summary of the implications for both dynamics and for the accuracy of ephemerides, which is of crucial importance to observers. So hopefully this will include in this talk something for just about everybody. 3-body resonances are rarer than two-body resonances. You can only look at certain systems with at least 3 planets to test for three-body resonances. But the key thing is that standard 0th order three-body resonances depend only on the orbital periods of the planets, not on the precession of apses or regressions of nodes, which are intrinsic features in all two-planet resonances. And therefore, since orbital periods are very precisely measured, in principle with Kepler, we should be able to do a much more accurate study of three-body resonances than we can of two-body resonance. And the resonance condition is that this combination of the periods of the planets, with P and Q being positive integers, is 0. Not is near 0, but is 0. Now, we changed this around. We normalized it. We switched it to 2 pi over periods. That's n, the mean motion. And we're normalizing it by the mean motion of the middle planet, just because if the planet is far out, then its mean motion is a lot slower. And even if it's not really close to a resonance in a fractional sense, you'll get a small number. So we did this normalization to really see what systems look like they are in three-body resonances, which ones are close. Here I show distributions of the systems near resonance. And the strongest resonances should be P plus Q, P and Q, both small numbers. And that we see in red. Now, if you are just drawing random periods, what you would get is that this curve should be roughly linear and intersect with the origin. And for the larger P plus Q values, the gold, green, and blue curves, that's what they pretty much are, with some statistical variations. It's quite clear that the red curve has a substantial excess near 0. And this is the three-body resonances. Great. But if you look a little more carefully at those points, most of them are not consistent with being 0. Only a few are. And some that have low values have extremely low formal uncertainties with periods from the KOI catalogs. And this is just not consistent with them being in three-body resonances if those are really the mean periods of the planets. And some of these are known to be in three-body resonances. These are some of the iconic resonance chain systems are included here that don't have uncertainties encompassing 0. So what's going on? We have to look at this in more detail at what goes into estimating the periods. So in measuring orbital periods of Kepler planets, the standard thing to do is to assume that the scatter is just random scatter. You get statistical noise, TTVs, you just lump it all together. You try and fit it with a best fit constant period. You're neglecting any real TTVs. And with this, you get extremely precise periods. The fractional uncertainties in the orbital periods rarely exceed 1 part in 100,000, and 1 part in a million is typical. 2 minutes in 4 years. Because you get a lot of transits for most Kepler planets. Now, that's the standard way to estimate periods. You have that for well over 4,000 KOIs. Holzer et al. Did a study of multi-planet systems and found that 199 planets could have their TTBs fit by sinusoids. And they fit a constant period plus a sinusoid, allowing any phase or amplitude of the sinusoid. So if there's an integral number of periods, that's going to be the same as a standard fit. But if there's say 1.5 periods, this would compensate for that extra half period that isn't included. Well, that doesn't work that well either, but we'll take a look and compare these. So first, we're going to look at a comparison between the constant standard fits periods and the sinusoidal fits. And then we're going to look at some of the dynamically solved systems. These include many of the iconic systems. And the techniques often yield very statistically significant differences in orbital periods. So here I show a comparison between the differences, the fractional differences between the KOI tables and the Holzer fits on the vertical axis, and the uncertainties in the standard TTB fits. These plots are just zoom ins to near the origin. Since there's such a dynamic range, I can't really show it on any plot. But what you have in each of these plots, if you're below and to the right of the green diagonal lines, the uncertainties in the catalogs exceed the difference between the two periods. If you're above to the left, then the two periods differ by more than the formal uncertainty in the catalogs. And the formal uncertainty in the sinusoidal fits are shown by error bars. In many cases, you don't even see those. We don't know why those formal uncertainties are so small. But clearly, a lot of planets are well to the left of the diagonal lines, and this implies that they have more uncertain periods. So now I'm going to look at some of these iconic systems, and they're different type. Many of them are in resonances, but they're all have substantial TTVs, and these TTVs have been used to get dynamical solutions for the systems. Kepler 11, green in all these plots is the measured period. Then you see the dots are transit to transit periods. The lines in the left plot are the average period over 4 years. Then on the right plot, you have average periods over 4 years and how that changes with time. And it changes by much more than the formal uncertainty. The red, blue, and black are 3 samples from photodynamical fits. And I'm just going to run through these for several systems, 1 planet in each system. Here is an actual resonance system. This is the resonant chain, KOI 730. And again, you see variations in the bottom plot in the 4-year average periods that are much larger than the formal uncertainties. So Kepler just measured a period at a given time it didn't measure the average period. Here,
Jack, you probably wanna get to the end of the talk. We're about to run out of time.
Two-planet system, much bigger variations than the uncertainty. Just another system, big variations on some time scales. And here I will show you my conclusions. The catalogs list orbital periods that are fairly straightforwardly derived. They don't account for various dynamical effects, and the dynamical effects can mean the long-term periods are many formal sigma away from tabulated periods. And you need to be very careful if a planet hasn't been observed for a long time and you're trying to make an observation with a big telescope. You want to make sure that you get the ephemeris right. Thank you.
Excellent. Thank you very much. And yeah, an important thing to have in mind for all observers out there. I can use my chair rights to pose a question. So what is the solution to the issue of having large uncertainties on planets that show TVs? Is there a way to deal with that for observers, for instance?
Well, you want to look at the system and you want to try and characterize the TTVs. And if you have enough information, you do a dynamical solution for the system. And this is something that sometimes, if you're going to use a very expensive telescope, big or in space, if you can observe it from a smaller telescope to get a more transit near the epoch, that can be very useful. If you don't see TTVs for 4 years, you're probably not going to have a huge effect on 10 years. But that doesn't mean you're not going to have a huge effect on 40 years. So to the extent we can follow up and get additional TTVs, additional transit times. So I want to second Lauren's request for Plato to do a long stare, and that long stare would do the best both for TTVs and for occurrence rates if one of their long stares puts the center of their field where they have the most glass on the Kepler field.
All right, excellent. Thank you very much. We'll move on quickly to the next speaker, which is Radek Poleski from the University of Warsaw. Radek, when you can share your screen, please go ahead and also unmute yourself, of course. So we're going to have a little bit of a change of gear now. We're going to talk about cold ice giants. So we're going to talk about the occurrence rate of extrasolar ice giants. Take it away.
Good afternoon, everybody. My name is Radek Poleski, and I'm going to talk about the cold and low mass planets, meaning the extrasolar ice giants and their occurrence rate. So we have Uranus and Neptune in our solar system, and these are two ice giants that definitely exist. And we would like to know, how did they form? It's hard to form them in situ. So definitely any planet formation theory that aims at explaining whole solar system formation needs to explain both Uranus and Neptune and their current masses, radii, and locations. So we can discover them around other stars, and here's an example. That's a microlensing planet from event called Ogle 2008 Bulge 92, and I will call it 92 for short. What we have seen is a standard microlensing event caused by the star, plus a short anomaly at the beginning of the event. The anomaly is short, so I'll zoom in and show you the data points taken over the anomaly itself. And just by looking at this plot, we can directly say that the system that lends the source light was composed of a star and a planet on a white orbit with relatively small mass ratio. We see that the timescale of the anomaly is short compared to the timescale of the main event, and the square of these timescales give us the mass ratio. So in this case, the mass ratio has to be very small. Also, we see that the anomaly is well separated from the main peak in relative to the length of this main peak. And this tells us that the planet is well separated from the host in units of Einstein ring radius. So just to be more specific, the mass ratio is 2.4 times 10 to the negative 4, and the planet-star projected separation, S, is 5.3 plus minus 0.1. And it's in units of Einstein ring radius. And if you're not very familiar with microlensing and you want to translate these to the astronomical units, then just multiply S by 2.5, which is the typical size of the Einstein ring radius in astronomical units. In this case, the Einstein ring radius was slightly larger, so the projected separation of the planet is 15 plus minus 4 astronomical units. And this estimate comes from galactic model. It's not direct measurement. S is directly measured. And also this galactic model is needed to constrain the host mass, which is 0.7 solar masses, and the planet mass, which is a few Uranus masses. So this planet is an extreme microlensing planet in the sense that among white orbit planets, it has the smallest mass ratio. Another example looks like that. I'll call this even 173 for short. So once more, we've seen the typical microlensing event caused by the star. And at the very end, we see this short anomaly. Here we have zoom in on our data taken during the anomaly. In this case, the planet is slightly closer to the star, 4.7 in separation, and the mass ratio is twice larger, though still significantly smaller than, let's say, Jupiter to Sun. So I've showed you that two examples of the very wide orbit planets. And just looking at these plots, we see that in both cases, we've seen the signal from the star and the planet. Though we may imagine that the source star did pass close to the planet, but has not passed close to the parent star. In such cases, we would see signals that look like this one. This is candidate free-floating planet that we published a few months ago. It's the shortest microlensing event ever found. It has timescale of just 42 minutes, and we don't see a significant other signal over many years. So it's a candidate free-floating planet. We cannot be sure it's a free-floating planet because there might be a host star, which we just don't see by chance. Though, for sure, in order to estimate the true rate of free-floating planets, we need to take the rate of the candidates and correct it for the number of cases where the planet is bound and we just don't see the host star. If you want to hear more about free-floating planets, just wait a few minutes and you will hear the talk by Przemek Mróz, who will tell us more about that. Okay, so my goal is to estimate the number of wide orbit separation planets. So I start with survey sensitivity, which is the number of planets we should have detected if there's one planet with given S and Q per star in the galaxy. I use 8 years of Ogle 3 data and 10 years of Ogle 4 data. The best cadence in this data is 20 minutes, and in many cases, it's poorer cadence. I've selected high-quality events, and the sample consists of 3,000 events. For each of them, I measured the sensitivity for planets that are in separation between 2 and 6. And I require that I detect both the peak from the host star and the planet itself. In the sample, there are 6 planets. Here are their short IDs. And please keep in mind that the stars I'm probing are low mass planets in the galaxy. So here are the detected planets. I'm using the plot of separation S versus logarithm of mass ratio. These two planets are the ones that I've showed. Here is 92 and here is 173. So the result of the calculations looks following. We have the survey sensitivity color-coded. As one can expect, the survey sensitivity is the lowest on the order of unity or even smaller in the right bottom part of the plot, meaning the widest separation and the smallest mass ratio. When the separation gets closer to unity and the mass ratio gets higher, then we expect more planets to discover. So one thing we can spot from that plot is that we have small survey sensitivity to these planets on the order of 1 or so, yet we detected 2 of them. So the number of planets with separation of 5 and mass ratio of 3.5 or 4 times 10 to negative 4 seems very high. They really seem to be very common. One may say that each star in a galaxy has a planet like that, and this statement is completely consistent with the data at hand. The other thing we see is that for separations larger than 4, we don't have planets with mass ratios between 10 to negative 3 and 10 to negative 2. There are other microlensing data that show planets over here, yet none of them shows a planet over here. For somehow more quantitative statements about these results, I would like you to divide the plot into 3 mass ratio bins and analyze them separately. So 2 days ago, Daisuke Suzuki told us about the mass ratio function he derived using MOA data a few years ago. And it's given by the multiplicative constant times mass ratio power to more or less negative -1 and times separation power to 1/2. There's a change in the slope for smaller mass ratios, but it's not important here. When I apply this planet occurrence rate to the survey sensitivity that I have, I found that I should have discovered slightly more than 1 planet with these assumptions. I found 6, so it seems that for Y orbits, the number of planets is larger than this prediction. One more thing I did was to estimate the multiplicative constant A separately in each of those mass ratio bins. And what I found is that the this constant is first around 5, then it drops in this intermediate region, and then it goes up once more. So to sum up, we need ice giant exoplanets to understand formation of our own solar system and to find the true rate of free-floating planets. Microlensing has already revealed planets that have orbits and masses similar to solar system ice giants, and it seems that low mass, wide separation planets are very common. Thank you.
Excellent. Thank you very much, Radek. So we'll just wait and see if a few questions will take into the Q&A. But I can start off with one. So how does your, let's say, preliminary occurrence rates, how do they match the predictions by Suzuki, for instance, in 2016?
Yeah, so it seems, just by saying that applying Suzuki occurrence rate and the survey sensitivity, I should have discovered just slightly more than 1 planet, and I found 6, meaning in this part of the parameter space, the A components should be larger by a factor of 6. So that's one thing we can tell.
It seems like you don't want to say anything too controversial here, so I won't make you say it. But would you agree that here it seems like there's definitely a dearth of planets between the Neptune size or Neptune massed ones and Jovian type giants?
Yeah. In general, analogs of Jupiter at much wider separations would seem to be very rare, for sure.
All right, we have one more question from David Bennett saying it would be more effective to change the M parameter in the Suzuki 2016 model. So that's something you can take into account as more of a comment.
So let me slightly comment on that. Yes, one problem is that I focus on these wider separations, and for sure Suzuki had a much wider range of S values that they probed. But yes, it's also a good idea.
All right, thank you very much. We'll move on to the next talk. There's one unanswered question that you can have a look at over in Slack. So the last talk of the session today is given by Jimmy Gross from Caltech, and he will be talking about the frequency and properties of free-floating planets.
Okay, I hope you can see my screen.
Looks good.
For those who don't know me, I'm Przemek Mróz. Currently, I'm a postdoc at Caltech, and today I'd like to tell you about my work on searching for and studying the properties of the population of free-floating planets in the Milky Way. By talking about free-floating planets, I mean planets that are not gravitationally bound to any host star. And from the theoretical point of view, free-floating planetary mass objects can be formed either through gravitational collapse in a way similar to that in which stars form, or they can be formed around stars in protoplanetary disks, and they are subsequently ejected from the parent planetary systems as a result of different processes, such as interactions with other planets, interactions with stars in stellar clusters, stellar flybys, and so on. The former process is more likely to produce giant Jupiter and super Jupiter mass free-floating planets, whereas the latter is more likely to produce lower mass, terrestrial mass free-floating planets. So how to find them? We use for that gravitational microlensing. Microlensing occurs when the light from a distant star, known as a source, is bent and magnified in the gravitational field of an intervening lensing object. And so observer on Earth will see a temporary brightening of an otherwise constant star. We call those brightening gravitational microlensing events. And what is important is that microlensing doesn't depend on the brightness of the lens. And so it allows you to find objects that are dark, that do not emit any light, objects such as black holes or planets. Every microlensing event has a characteristic angular scale, which we call an angular Einstein radius, which depends on the mass and distance to the lens. Basically, when the lens and the source are perfectly aligned, the source will appear as a small ring with a radius equal to the angular Einstein radius. Unfortunately, for the great majority of microlensing events that we see, we cannot measure the angular Einstein radii. And the only physical parameter that we can measure are their timescales, which also depend on the relative lens source proper motion. However, on average, timescales of microlensing events depend on the mass of the lens. Basically, the lower the mass, the shorter the event. And so typical microlensing events that are caused by stars have timescales on the order of 20 to 30 days. Microlensing events by Jupiter mass objects have timescales of about 1 day, and microlensing events by Earth mass objects are extremely short. They have timescales of just a couple of hours. So if you have a large sample of microlensing events and you measure the timescales precisely, you can get information about the mass function of lenses, including masses of free-floating planets. So I analyzed a sample of microlensing events that was detected by the OGLE survey, which is one of the largest and longest running sky variability surveys. Currently, OGLE is in its fourth phase, in which we are observing the densest regions of the sky, including the galactic center and the galactic plane. In particular, some of our fields toward the galactic center are observed at a very high cadence of either 20 or 60 minutes. And such a high cadence allows us to detect extremely short timescale microlensing events that may be due to planetary mass objects. And the goal of my work was to detect microlensing events in our high cadence fields, measure the timescale distribution, and then infer the frequency of free-floating planets based on these observations. So this plot shows the distribution of timescales of microlensing events that we found. This distribution is already corrected for detection biases because it is, of course, much easier to find long events than short ones. And the vast majority of microlensing events that we see are caused by brown dwarfs and stars. There's not much room for Jupiter mass free-floating planets. So we got an upper limit on the frequency of Jupiter mass free-floating planets of 1 per every 4 stars. Thus, we do not confirm earlier findings, which claimed that there are 2 free-floating Jupiters per every star in our galaxy. We also found 6 extremely short timescale microlensing events. They have timescales between 0.1 and 0.4 days. And such short timescale events should be caused by low mass Earth to Neptune mass objects. And because our sensitivity to such short timescale events is very low, our detections are consistent with such low mass planets being more common than stars. So for all of these detected, for all of these events, the only physical parameter that we could measure were the timescales. So in principle, short timescales may have been caused by large relative length source proper motions. So to verify, to check whether our objects are indeed very low mass planets, we needed some additional observations. We needed measurements of the Einstein radii of our lenses. Unfortunately, that's possible thanks to the so-called finite source effects. So usually when you think about microlensing in the Milky Way, you can treat source stars as points, which means that typically Einstein radii are much larger than the angular size of the source star, and the whole light from the source star is magnified. However, as the mass of the lens gets smaller, the size of the Einstein ring becomes smaller, and at some point it can become comparable to, or even smaller than the size of the source star, in which case only a small fraction of the source's area is magnified, and the light curve shape gets distorted. So here are some example light curves for a microlensing event by a 2 Earth mass object. Depending on the size of the source star, the light curve looks differently. And by measuring the shape of the light curve, by modeling the shape of the light curve, we can measure the size of the Einstein ring. And so we have much better constraints on the mass of the lens. And this is why we carried out dedicated searches for very short timescale microlensing events with giant sources, because we hope to find some events exhibiting finite source effects. And these efforts proved to be very successful, as now we have several very strong free-floating planet candidates. Our best candidate is OGLE 2016 BLG 1928. This is the shortest timescale event ever found, with a timescale of just 42 minutes. The light curve of this event shows very strong finite source effects, from which we could measure the size of the Einstein ring of 0.8 microarc seconds, which corresponds to the mass of the lens about 0.3 Earth masses, which is 3 times the mass of Mars. So far, this is the shortest timescale microlensing event ever found, and the lowest massed object ever found using microlensing. Another example, OGLE 2012 BLG 1323. This event has a slightly longer timescale of 0.15 days and a slightly larger Einstein radius of about 2 microarc seconds, from which we could estimate the mass of the lens to be 2 to 15 Earth masses. We have 4 other strong free-floating planet candidates. All of these events have timescales between 0.2 and 0.4 days, and Einstein radius smaller than 10 microarc seconds. So again, these detections support our earlier results that such low mass planets are more common than stars in the Milky Way. So as Adek mentioned, there's one caveat. We are not fully sure whether our objects are indeed free-floating or not. And this is because microlensing allows us to detect stellar companions within about 10 astronomical units of the planet. So if there is a more distant stellar companion, we won't see it in the microlensing light curve. We need some additional follow-up observations. For example, we can get high resolution images of our lens and source several years after the event, when the lens and the source separate in the sky. So if there is some excess of light at the position of the lens, this will tell us that the planet has a stellar companion. It's not free-floating. It is on wide orbit about some star. If we don't see any excess of light at the position of the lens, this will tell us that the planet is likely free-floating. So currently, current lens source separations are very small, are smaller than 50 milliarc seconds, and they are practically impossible to resolve with the current technology. But all of our free-floating planet candidates can be checked for host stars in the future with the next generation of adaptive optics on the next generation of large telescopes. So this will be possible in several years, in about 10 years or so. Looking further in the future, we think that the planned Roman Space Telescope will have very high sensitivity to short timescale microlensing events, and we expect that Roman should detect dozens, if not hundreds, of free-floating planet events by free-floating planets. But I think that Samson Johnson will tell us more about that on Friday. So to sum up, we can detect free-floating planetary mass objects using microlensing. Our current observations indicate that free-floating Jupiters are significantly less common than previously claimed. So there is less than one free-floating Jupiter per every 4 stars. However, we see some evidence for a population of lower mass free-floating planets like Mars to Neptune mass objects. Okay, thank you.
Excellent, thank you very much. I really like the name Rogue Mars for that low mass one there.
Yes, you can be floating or rock.
We have a few questions over in the chat. So the first question is about how do you estimate the masses of these free-floating planets? Are they all based on the galactic model, or do you actually have how do you get it?
Yeah, so the only observable is the Einstein timescale, which depends on the mass and distance to the lens. So we can also measure the proper motion of the source star using Gaia, and we can also measure the relative lens source proper motion using microlensing observations. So proper motion observations give us some hint whether the lens is in the disk or in the bulge. So we have some rough idea about the distance to the lens. So in the case of our Mars mass candidate, we are pretty sure that the lens is located in the galactic disk because its proper motion, the proper motion of the lens is consistent with proper motion of stars in the galactic disk. So we could like pinpoint the mass of the lens to be something about a few times of Mars. But in the case of other events, we're not fully sure whether the lens is located in the bulge or in the disk. So currently we cannot measure masses. This will be again possible with the Raman telescope with simultaneous observations of the same microns given by Raman and by some ground-based observatories. We think that such concurrent observations should allow us to estimate masses of lenses.
All right, thank you very much. There are a few other questions in the chat, but I think we will move them to Slack in the interest of time. Yeah, so thank you very much to all of the speakers of this session. I think it was very interesting and stimulating. And I'm gonna hand the Zoom microphone back to the organizers for just a few seconds.
Thank you so much, Louise, and to all the speakers. All right, everybody, you know what I'm going to say. Get up, stretch, have some hydration, head to the Slack. There's heaps of questions from this session. Head to the Wonder Room and chat with folks. I put the link in the chat. Today's zine came out a little late, but it's out now. Should be in your email or in the Slack if you didn't get an email. And don't forget to register for tomorrow night's Science Fiction Writers panel if you're excited. We're about 3 minutes late, but let's just reconvene at the top of the hour so we can keep to the schedule. So see you back here in 27 minutes for architectures from the theory point of view. Hey, Jehan. I don't have any announcements for the top of the hour, so feel free to just take it away when it gets to 1 o'clock.
Okay.
Jesse and Jehan, could you remind me who I should pin to get the timer?
I believe it's Ellen. Ellen, should Eve pin you?
Yes, yeah. I'll start sharing my video when you start your talk, Eve.
Okay, so there's two of you. Which one should she pin?
Here, let me pin this one.
Yeah, so pin that one. It's good to see you, Eve.
Yeah, how are you?
Good, good. I'll be better next week.
Oh yeah, I'm sure. Thank you so much for doing everything and in these crazy times.
No worries. I could not have known a year ago that this would be what the times would be. So I'm glad it's working out. I'm glad we're managing to make it work. All right, but I'll let Jehan start the session.
Okay, it's 1 o'clock, so let's get started. Welcome back, everyone. My name is Jehan Bae. I'm a postdoc at Carnegie Institution in US. I just wanted to remind you that this conference is being recorded and you can ask questions through the Q&A feature in the Zoom webinar, and you can also do so anonymously if you wish. Okay, with that, oh, actually I have one announcement. After the last talk of this session, there will be one more poster pop. So if you want to listen about posters, please stay on. With that, we will get started. So we will be continuing to talk about architectures of systems, but from a theoretical point of view. And the first talk this session will be given by Eve Lee from McGill University, and she'll be telling us about using radius-dependent occurrence rate profile to reveal formation pathways. So if you are ready, Eve, you can share and start.
Okay, could I double check with everyone that the slide is showing up as it should?
Yep.
Yeah, it looks good.
Okay, great. Thank you so much. Thank you, Jehan, for the introduction, and thank you so much for all the organizers for making this conference a reality. So Scott Gowdy, on Monday, opened this conference by telling us about the importance of careful characterization of exoplanet demographics because it gives us a window, a probe into revealing the formation pathways of all these exoplanets that we detect at present. And when we are talking about the planet formation, like where and when do they form, which tells us how they form, we have to think of them in the context of the evolution of their underlying disk. So some of these planets may form really early when there's lots of gas around. These are the kind of environments where you expect the formation of massive gas giants. These are also the kind of environments where you expect the circularization of the orbits due to the dynamical friction of the gas, as well as a generally inward migration as the planet tidally interacts with the nebular gas. But some of these planets may form really late just as the disk gas dissipates. These are the kind of environments where you would naturally expect the formation of smaller planets. So I'm talking about sub-Neptunes. And these are also the kind of environments where you expect the perturbation between the multiple planets within a given system so that there could be orbital crossings of the different orbits and the series of giant impacts and a series of collision and mergers that can facilitate further growth of these planets. And another important thing about the late time formation is that there's not enough gas around to torque these planets towards the central star. So these are the kind of environments and the time scale over which we would expect in situ assembly. So for this talk, and I would encourage everyone to think about when we compare the migration scenario versus in situ scenario, I would advocate for thinking about them in the context of the evolution of the disk. But we are at a conference about the exoplanet demographics. So how can we use these observables to distinguish between migration and in situ assembly? they typically use the distribution of orbital period ratios, in particular because the standard expectation of large-scale migration is that the multiple planets should lock into mean motion resonance. Although there are some caveats which I'm gonna go back to later during this talk. And what we've learned from Kepler is that the distribution of orbital period ratio is just way too wide, as would have been expected from migration. But I would also say that we can use something simpler. We can use the distribution of orbital periods themselves. So of course, many different groups have carefully characterized the occurrence rate as a function of orbital period and the radii of the planets. And they all use different methods, like different ways in which you can characterize the detection uncertainties, biases, as well as the transit probabilities. And many people during this conference have told us about how you need to be very careful about those. But I am heartened to see that in general, the shape of the orbital period distribution has been pretty much constant between different groups. So basically, if you see the small planets, so I'm talking about sub-Neptunes, they tend to be pretty flat in terms of log orbital period. And of course, there's a bit of a break at 10 days, and the power law, the slope, it falls off much more sharply at closer in orbital periods. And what I found very striking from these plots is that the shape changes considerably once you look at these larger planets, so sub-Saturns and Jupiters, where you don't see this plateau. It just keeps going up at least out to 300 days. So why is that? Can we leverage these different profiles to distinguish between the different formation pathways that create these different types of planets? So let's first take a look at the small planets, this flatness in log orbital period first. This can be naturally explained by in situ assembly because dynamical stability tells us that these planets have to be spaced apart by some factors of mutual Hill radii. So basically, the farther out you are from the star, they have to be spaced apart farther from their neighbors. So these small planets probably, maybe, more likely to have assembled late and in situ. These are also the kind of environments where you can naturally produce these small planets because there's not enough gas nor time to engender these large gas giants. But let's look at this further. There's this break at 10 days. How do we explain this break? What is interesting is that this break at 10 days and the shape of this fall off is very reminiscent to the distribution of the stellar rotation periods in nearby young star clusters. So perhaps we have fewer planets around the stars at this close in orbit because you're basically reaching the inner edges of the disks, assuming that disk inner edges are near co-rotation with respect to the star. And that idea has some theoretical backing. So this comes from the idea that there is a force balance initially between the stellar magnetic pressure, so the magnetic pressure from the stellar magnetic fields that are threading through the disk from the star that's trying to push the material away. But we know these disks are accreting. We observe this. So that means there's a ram pressure, and the disk would truncate initially where these two forces balance. But there's also an angular momentum transfer between the spin of the star and the orbital motion of the disk, so that at equilibrium, you would expect the disk to truncate near co-rotation with respect to the star. And I have to say, from a theoretical perspective, there's a lot of work still needs to be done in characterizing carefully the dynamics at these inner edges of the disk. But there is an observational evidence of disk truncation near co-rotation given by these dipper stars, which are young stars where you see these periodic dips, which tends to be at about the same periodicity of the star spot, so the spin of the star. And these huge dips in the light curves are given by those dust clumps that are orbiting at near the inner edges of the disk. So based on that, we can now try to quantitatively compare the expectations from the in situ assembly to the large scale migration, where the question here is, are the current observables sculpted largely by the final in situ assembly, or do we retain that initial memory of this large-scale migration? So for the in situ, this is super simple. What all you do is you just sprinkle a whole bunch of planets for a given system somewhere between the inner edges of the disk, drawn from the stellar rotation periods out to about 400 days. And again, randomly distributed in log orbital period. And what about migration? You start from the same setup, but now you let the planets undergo inward migration as they tidally interact with the surrounding disk. What's important with the migration is that you need to decide what happens at the end, especially when the innermost planet parts at the inner edge or close to inner edge, where it depends on how exactly the shape of the inner edge looks like. So the classic expectation is that these planets would enter and stay in mean motion resonance, although this actually depends on both the parameters of the planet and the disk. You need the migration timescale to be slow enough. It has to be slower than the libration timescale of the resonant angles. So there could be some cases where you actually break out of the resonance. And if that's the case, then you would expect some sort of a mergers at the inner edges. So these are the end member cases, and we can now compute the expected profile of the occurrence rate as a function of orbital period and compare the model to the data, where the models here are given by curves and compared to the data given by the circles. So in situ assembly, we see this flatness as we've seen in the data, and the break and the fall off as we're probing these inner edges of those protoplanetary disks, which looks very similar to the data. For the large scale migration, it does not do as good of a job. This curve over here is just going to continue to go up if you extend this to longer orbital periods. Although I will have to say that this exact shape does depend on the disk structure. And I'm going to come back to this later during this talk. But what's more important is that with migration, you do expect some pileup with respect to the data, because that's what migration does. You are simply transporting the planets that are farther out to closer in. And as long as they undergo this large scale migration from their origin point to the inner edge, you are going to see this pileup, which we don't see the signature of in the data. But for now, I would like to draw your attention to these ultra short period planets with orbital periods less than a day. So it's extremely hard to create these planets as such short orbital periods. So they need some sort of tidal interaction. It could be due to tides raised on the star, which causes a tidal in spiral. But for that to work, you require some of these ultra short period planets to have already started at slightly less than a day orbital period. That means these planets, the progenitors of these planets, were born around rapid rotators. Or you can have tides raised on the planet, and especially if you could perturb these planets onto more eccentric orbits, those eccentricity tides could be the dominant process. And we do see this observed hint of a perturbation by outer bodies. And we do see for this ultra short period planets in multiplanetary systems, they tend to be more puffed up in terms of their mutual inclination. So what are these perturbers? Could it be outer gas giants? One issue is that you need at least two, and they themselves need to be dynamically hot. Perhaps what's more comfortable is that you can use the nearby smaller planets in multiplanetary systems due to the secular perturbation, and in particular secular chaos. And there have been multiple groups who have actually calculated that for a typical Kepler multiplanetary system kind of architecture, you can indeed drive the high eccentricities of the innermost period planet. And due to tidal circularization, you can drive them onto the smaller, less than 1 day orbital period. Okay, so we've talked a lot about the distribution of the orbital periods themselves. Let's go back to the period ratio distribution, where we've already seen that the observed distribution is just too broad for large-scale migration. And of course, there have been multiple hypotheses in trying to reconcile that with the migration theory. One idea is that even if some planets may enter into mean motion resonance, that might be unstable because of eccentricity damping, again, due to the interaction between the planet and the disk. Although that depends on the planet and the disk parameters. And furthermore, I'm not going to talk too much about it because Nick Choksi later during this session is going to tell us all about it. So please go to his talk. And another hypothesis is that all of these planets do enter into mean motion resonance, but they subsequently undergo orbital instability once you get rid of all the disk gas. One problem here is that there is no clear way to robustly predict the fraction of the systems that do undergo instability. You do need a very high number, but not 100%. And of course, another idea is that the planets were actually never in mean motion resonance to begin with. But again, I'm not going to belabor the point. Please just go to Nick Choksi's talk to learn more about it. Okay, so coming back to the orbital period distribution, we have begun this discussion looking at those small planets. And we've talked about how this flatness and this overall shape can be explained by more late time in situ assembly. But what about this difference in shape between the small planets and the large planets? Why is it that for this large planets, the occurrence rate just continues to go up towards larger orbital periods? Could that be due to this different formation processes, like perhaps they actually retain this initial memory of migration? And in fact, you can actually show that naively, this is actually what is expected. You can write down completely analytically what the orbital period distribution needs to be, as long as you reach some steady state. So for example, in steady state, the number flux through all these orbital bands are constant. That means the relative ratio, the relative amplitude between these different orbital periods are basically set by how long the planet spent at each given orbital period bin. So it is given by the migration timescale as a function of orbital period. And how do you calculate migration timescale? Well, why do planets migrate? It's because the planets are losing angular momentum to the disk. So you can just calculate this by dividing the planet's orbital angular momentum divided by the tidal torque. And calculating tidal torque is also pretty easy, as long as you remember the Chandrasekhar dynamical friction formula, which is this, and then you have to account for the cancellation between the outer torque and the inner torque in a gaseous disk, which has a pressure support. And it's a torque, so you just multiply the force by the orbital distance. And if you combine everything, then you can find the shape of this orbital period distribution as a function of the disk structures. So this is actually pretty sensitive to the gas surface density as well as the temperature profile. And which also means as the planet grows, it can create all these substructures within the disk. And there's a lot of disk physics that also goes into this. And it can create a lot of issues and a lot of challenge to the migration hypothesis. But for that, please just go to Tim Hallett's talk to learn more about it, which is coming up in this session as well. Okay. So small planets, perhaps naturally explained by in situ. It can also explain the fact that they are small. And for large planets, they require formation in the early stages. And perhaps this orbital period distribution could be due to migration, but there can be a lot of challenge, so perhaps not. But for now, let's talk about this relative occurrence rate between the small planets and the large planets, this amplitude. Why is it that in our galaxy tends to favor these smaller planets as compared to these large planets? And why is that the case? You can see this more clearly if you look at just the histogram of the radius. And the data are actually shown in the grays. And there's a very sharp cliff right at around 3 to 4 Earth radii. And why is that? Well, there is one very nice result from Edwin Kite's group. Please go see Edwin Kite's poster, to learn more about this. But to summarize it very briefly, the idea here is that there's a core envelope interaction. So as the core just continues to accrete gas, you just dump gas onto this planet, the core envelope boundary becomes hotter. It also becomes more pressurized, which facilitates the dissolution of the gas into the core. which means you can hide a lot of gas into the core so that once you go past a certain point, you can't just keep puffing up planets by adding gas onto it. So that might be why. Or so perhaps more a standard way is that if you look at the formation criteria of these large planets, first of all, you need massive cores. Second of all, they really have to assemble very early. So perhaps the fact that you have a cliff just tells us something about the difficulty in which creating this massive cores early enough. So how do we test this? How do we go about testing this idea? Well, you do need core mass distribution, which can be hard to measure. But recently, there have been a lot of great work trying to back out the core mass distribution from data. In particular, you start from the radius distribution because we just have a lot more data for the radii. And then people have been forward modeling the different envelope mass loss models to back out the best fit core mass distribution that can reproduce the data. And this was motivated in particular by this beautiful result from CKS as well as astroseismology of this radius gap, which I believe Ryan Cloutier has talked about in detail yesterday during this conference. And the fact that there is a gap in this radius period space has been considered as the smoking gun signature of the envelope mass loss. And to hear more physics behind that, I do encourage you to go see James Rogers' talk as well as Akash Gupta's talk later during this conference. All I'm gonna say for this is that if you look at this best fit core mass distributions, they tend to be very peaked, especially for photoevaporation models. But about the same thing with the core powered envelope mass models as well. And in particular, they tend to be peaked as compared to the current RV measurements. And I haven't applied any corrections, any detection biases to this mass distributions. So it is possible that we may be missing a lot of small mass objects. And we've seen the hints of this as well in the radii distribution as being computed by David Su et al., I believe last year. So how do we reconcile this? Well, one issue is that these models have been assuming that all the cores, even the tiny ones, they start with a few percent by mass envelope, but not all cores can accrete so much gas. And this has been alluded to by Kevin Schlafman, I believe on Monday. But let's talk about the physics behind that. So how do planets actually accrete gas? Well, it's mediated by, at least initially mediated by thermodynamics. So if you have some rocky core in a nebula, then any gas within its gravitational sphere of influence will be bound to the core, but that envelope is going to cool and contract. But this process will terminate if the envelope maximally cools to an isothermal state. In other words, it has completely thermally relaxed to the outer nebula. And if you calculate this isothermal maximum mass for a given core at a given distance from the star, you will always see that the cores that are less than about 1 Earth mass will never be able to accrete enough gas to be sub-Neptunes. And in fact, because this isothermal mass is sensitive to how hot the surrounding nebula is, the radius gap, which this is all naturally produced by just gas accretion alone, the position of the gap actually moves towards larger radii, towards closer in distances and orbital periods with respect to the star. And you can actually look at this more systematically, and using a very broad core mass distribution, which has been best fit to the current RV measurements, then just from gas accretion alone, you can create the radius gap in both the 1D space as well as the 2D space. And this, the slope over here, it is actually in agreement with the current measurements. Okay, so what are some observational tests? So first of all, I would submit this as an evidence that the observed radius gap, it is a very robust feature that is robust against the unknown efficiencies of all these different mass loss processes. But how can we test this? Well, it would be really great if we can actually have a broader or have more careful measurements of the core mass distributions. It would also be really great if we can have the measure of the abundance of these small planets beyond about a few tens of days. Okay, and I'm a bit running out of time, so I'm going to go through this very briefly. And so we've talked a lot about the smaller end of the core mass distribution, but what about the higher mass end of the core mass distributions? It's really difficult to get the core mass functions of giants, although Daniel Thorngren has told us about some ways we can do that. I would say we should really leverage the sub-Saturn population as well, because the sub-Saturn occurrence rate looks so similar to the gas giants. They probably have undergone similar formation processes. So you can actually use the sub-Saturn occurrence rate as a function of orbital period, because these sub-Saturns are not massive enough. They are actually susceptible to envelope mass loss. So that at given orbital period, you can calculate the minimum mass of the core so that a sub-Saturn can remain a sub-Saturn. Then based on the underlying assumed core mass distribution, you can calculate the expected occurrence rate at a given orbital period to create the overall distribution. Okay, so to summarize, we've begun the discussion with the orbital period distribution, as well as different ways we can leverage this different observables when it comes to exoplanet demographics to reveal the potentially different formation pathways of these kind of planets. So for small planets, we've seen that they can be naturally produced for planets that have assembled late time, more in situ. And for large planets, they require formation around massive cores in early stages. And right now, I would say it's a bit unclear whether they are by migration or something else. So where do we go from here? Well, we do need more occurrence rates farther away from the star, especially for the small super Earths. And we really do need to extend this further out. And furthermore, the formation of the planets, in particular, whether the planets can be small or large, that is very sensitive to how massive and when exactly you can assemble these cores. So in terms of the observables, we would definitely need more mass measurements, especially beyond 10 days, where we can really probe the initial conditions before the envelope mass loss processes. Thank you.
Okay, thank you very much for the review. We already have a couple of questions in Q&A. So the first one is the period distribution from planet migration really different from in situ formation? A series of planets locked in mid-motion resonance also have the flat occurrence rate distribution you attributed to in situ formation.
Right. So if you have the entire system being locked into mean motion resonance, then yes, you can. But if you consider the more broader distribution, so if you again, like so first of all, you do need the migration timescale being longer than the libration timescale of the resonant angles. So that requires the mean motion resonances are naturally reached when one of the planets actually park at the inner edge. That's why in the cartoon, you've seen just the inner few planets being in mean motion resonance and the outer planets not being in mean motion resonance. So definitely on the very inner regions, you can have a more flat slope. But on the outer regions, as long as you maintain the memory of the migration, you would see the larger occurrence rate farther out. Again, with the caveat that it does depend on the structure of the disk.
Okay, thanks. The next one is, do the different mechanisms for creating the radius valley make different predictions as to how deep or empty the valley should be?
Yeah. So for the core powered envelope mass loss and for evaporation, I would just encourage people to go to James Rogers and Akash Gupta's talk. But I can tell you about what happens for this scenario. So the depth here, it does depend sensitively on what the underlying core mass distribution is. And also if you apply starting from the radius valley, and if you apply some sort of a mass loss processes, then in a lot of cases, it actually makes things worse because you actually dump these planets onto the valley, and you actually, instead of carving out the valley, you can actually fill in the valley. So I would just say for the moving on from here, we should take more care into looking more carefully at the initial conditions of these planets as a function of the core masses.
Okay, we have a couple more minutes for questions. If we don't have anything else, I can ask you a question about migration again. So I guess my question would be, how sensitive is the outcome dependent upon the migration rate or migration speed? Because from the disk side, migration is something still very uncertain. It's, well, we are working hard, but it depends on, as you said, this dense distribution, temperature distribution, but also viscosity. And if they are in mean-motion resonance, convergent migration speed can be very different from single disk-driven migration. So, or conversely, can you put any constraints by looking at the exoplanet distribution on migration, how migration would have happened in the past?
Yeah, I don't want to steal too much thunder from Tim's presentation, but I can just like briefly mention that. So you're absolutely right. The overall shape here. So for example, if you had some sort of substructures that halt the migration or like partially halt the migration, then you can actually make this slope really flat. So I would say, like, if there's an independent way to say that this is like definitely due to migration, then you can then you will have to find a way to break. So let's say those substructures actually created more flat kind of distribution. Then, and you also further say that there's no way these planets could have not been sculpted by migration, then you'll have to look for ways to pull it back down to create this slope. And there are definitely ways to do it. You can use both the disk structures. You can also use the planetary parameters themselves. But I'm like purposefully saying this very vaguely because I want people to go to Tim's talk.
Okay, thank you. We have one last question. If great talk, can you remind me what is the difference between gas poor and gas empty planet formation, and which of these scenarios applies to the solar system terrestrial planets?
Oh, great question. So gas poor, that means, so the disk evolution is a continuous process, right? So when I say gas poor, I'm talking about the very, very later stages of the disk evolution, where the disk surface density has been depleted by, let's say, 2 orders of magnitude. So we're talking about like something kind of similar to the transitional disk. Gas empty formation is way after that, when you completely get rid of all the gas. So way after like 10 million years or so. So I would say for the solar system, the inner planets, I would say they probably have been the final assembly. I'm not saying anything about the initial assembly, but their final assembly likely occurred in those gas empty environments where the disk was completely devoid of gas.
Okay, thank you. With that, we will move on to next speaker, who is Martin Schlecker from MPIA, and he's going to talk about a compositional link between warm super Earth and cold Jupiters.
Yes, thank you, Jehan. Can you hear me well?
Yeah, great.
Cool. So it's a pleasure to be here virtually. I'm a PhD student at MPIA, working with Thomas Henning and Hubert Klar. And I'm excited to talk about multi-planet system architectures today and the connection between warm super-Earths and cold Jupiters. And I'm going to do that mainly from a theorist standpoint, because my results are based on a synthetic planet population that are produced by our planet formation model. And this model has mainly been developed by my collaborators in Bern. And so I really owe these people that you see on the slide there. This has really been a team effort. And I also think that a lot of exciting results that we already saw in the course of this week reminded us that planets come in a wide variety. But today I want to focus on 2 popular planet types: super-Earths on close orbits and giant planets far out. So I guess it's best to define these planets in mass period space, where of course there's no universal consensus, right? And so we also just adopted these mass period limits that you're seeing here from observational studies that reported a very interesting trend. What they did was they counted the numbers of systems that had either none of these planet types or only one or both of them. And they found that there's an enhanced cold Jupiter occurrence in systems that also have a super-Earth. Or mathematically spoken, the conditional probability of having a cold Jupiter, given there is a super-Earth in that system, is higher than the probability of finding a cold Jupiter in any random system. And it also seems to go in the other direction. So it seems that these planet types are somehow mutually, positively correlated. And of course, this doesn't tell us if once they form, they have some mutually beneficial influence on each other, or if they just rely on the same underlying conditions that maybe just enables efficient planet formation. The observations don't tell us this. And of course, there are also observational biases involved. And so the actual numbers might be debatable, but the non-correlation case really seems to be excluded. So can we understand this? Is this something that our formation models can reproduce? Yeah, I'll give away the answer and say that our model reflects the general trend, and there are some caveats that I can go into later. But we wanted to go one step further, actually, and ask, do super-Earth with giant companions differ from those without? Before we address this question, let's have a look at the model and at the assumptions that we did in our model that our results are based on. So this is a global model following the core accretion paradigm, and it's been continuously developed over the course of many years. So I can really just highlight some key modules and assumptions that we make that are most important for the results I'm presenting today. So this model combines the evolution of a viscous accretion disk, including photoevaporation. We have up to 100 protoplanets that concurrently grow in the same disk and that accrete planetesimals and gas. We also solve for the interior structure equations, which is very important for the long-term evolution of the planets. And if you want to compute transit radii gigayears after the formation, there's also orbital migration. And very important for the terrestrial planets and all the smaller mass planets, actually, n-body interactions between those up to 100 planets. And this really defines the final system architectures, at least for the lower mass planets. But particularly important for this project here is the compositional tracking. So we also keep track of what material these planets actually accrete, what kind of planetesimals are they accreting. We use an equilibrium chemistry model to track the abundances of iron, silicates, and ice. So back to the question, and to answer it, I will divide our synthetic population into two groups of systems. One group that has both planet types in each system, and one group that has only super-Earth but no cold Jupiters. Let's have a look. So here I plot these groups in semi-major axis mass space, and color-coded here is the fraction of water ice in the core of the planet. And we found then that on average, super-Earths with a giant companion have lower ice mass fractions than those without. So let's turn this argument around and say, if you have detected a super-Earth, you have measured its mass and radius, you've characterized it, can you use its position in the MR diagram to learn something about possible additional planets? So if we plot these two different groups or populations in an MR diagram, and here I'm plotting only the super-Earths, we can see that they indeed occupy different regions in this plot. So for your orientation, these two diagonal lines that you're seeing, at least in the lower plot, these are the cores without significant atmospheres, so icy or rocky cores. And already there you can see that this whole population of icy cores, it doesn't exist in the group that later on has only super-Earths but no cold Jupiters. But the difference is even more evident for planets with atmospheres. So this whole cloud of icy cores with significant envelopes just doesn't exist in the other group. So there seems to be a link between planet composition and system architecture. So that's an interesting prediction. And of course, we wanted to check if this is real. So we compared it with observed exoplanets. I'm going to overplot observed exoplanets, but only the group with super Earths and cold Jupiters confirmed, because the complementary sample is, of course, very corrupted by biases, because you never know, is there indeed no cold Jupiter, or has it just not been detected, at least not without much more effort to characterize the sensitivity of that study. So here I'm only overplotting those observed super Earths that also have a confirmed cold Jupiter in the system. And we see that it fits well the corresponding synthetic sample, the upper group, but it does not fit so well the lower one. So that's, of course, very reassuring, but also not an unequivocal proof of our prediction, for which I guess we have to wait until our MR diagram is more populated. And of course, that's increasing rapidly the sample of planets in that diagram with the current and future missions. And until then, I guess we can at least use our model to try and understand where this effect actually comes from. So how does this come about? That there's a connection between the composition of planets and the architectures of the resulting multi-planet systems. We found that it actually goes back to different disk properties, all the way to our initial conditions of the simulation, where the defining parameter is really the solid content of the protoplanetary disk. So the total mass of planetesimals that we give to the disk in the beginning, which is distributed differently for the two populations. So if we plot this distribution of that parameter for the familiar two groups, we see that systems that produce super Earth but no cold Jupiter, this is the red line here, they started with intermediate mass disks. So kind of like 100 Earth masses or a bit more, but those systems that in the end produced both planet species, they had a much more massive disk in solids in the beginning. And now we can connect the dots. So in the global picture, it can be best summarized in two formation channels, where the first case is that you have such an intermediate mass disk, but it has to be sufficient for planet formation, for super Earths to emerge. So 100 Earth masses or so is the ballpark here. In this case, primarily icy super Earths form. They migrate inwards to detectable distances. And we end up with systems of volatile rich planets of low bulk density, and no giants are formed. In the other case, where we have a high mass disk with several hundreds of Earth masses, we can form cores also further in, and they migrate to become dry super Earths. But the conditions are also right to form giant planets, and these would prevent icy cores that formed further out from migrating inwards. So in the end, we have only high density super Earth and a distant giant planet. So if this mechanism works the way I just described it, what are the implications of this? What can we learn from that? With pure planetesimal accretion, we predict that there is a positive correlation between those two planet types. But on the other hand, some pebble accretion models actually predict an anti-correlation here between super Earths and cold Jupiters. So we can use this result to constrain the efficiency of pebble accretion, or maybe the relative importance of pebble versus planetesimal accretion, but also the timing of when giant planets emerge in the system, because a giant planet would cut off a radial pebble flux at some point. Another aspect relates to planet migration. We find that outer giants and inner super Earths, they actually always form together when the conditions are right. But where super Earths are missing later on, these systems of super Earths, they have been destroyed by dynamically active giant planets. So by giant planets that migrated inwards into the warmer regions and became warm Jupiters. And one example of such an eccentric warm Jupiter is TOI 2179b. It's a very eccentric planet of 15-day period, which we discovered in full frame images of TESS. And we also found in this system that there are no stable orbits possible interior of that planet, no super-Earth orbits. But keep in mind that such objects are actually rare. So in reality, they're more rare than our simulations. This might be a hint that migration is not as efficient as proposed. So I hope I have convinced you that inner super-Earths and cold Jupiters are not independent from each other. And I want to finish with some key takeaways. First, super-Earths that have a cold Jupiter in the system are, on average, less icy than field super-Earths. And this leads to the prediction that those with a high bulk density can be used as proxies for giant companions in the same system. When we connect this result to the formation phase, we can understand where this comes from. If you have an intermediate mass disk, this enables the formation of icy super-Earths, but no giants form. More massive disks, on the other hand, can produce rocky super-Earths and can also produce giant planets. So once again, thank you for having me. Stay safe, keep distance to each other, but also stay clear of any eccentric warm Jupiters. Thank you.
Thank you for your talk, Martin. We have one question, well, two questions now. The first one is, nice talk, Martin. How are the super-Earth or mega-Earth of about 20 Earth masses without gas envelope forming your model?
Okay. Yeah, so I'm not sure where the question is exactly aiming at. I mean, they're just more massive super-Earths. I think I understand that this limit that we chose here, that this comes over as quite massive for a super-Earth, these 47 Earth masses. This is, of course, a lot of mass for a super-Earth, but in this case, we just adopted the limits for comparison with our observational studies. They form as the other super-Earths form as well in our model. So mainly
I guess if I can interrupt, I guess if you go to your mass radius diagram,
right.
I think there are few planets on the right-hand side which has 30, 40 Earth masses. I think it is what the question was referring to.
The bare cores without atmospheres, or?
Yeah, so those are those, I guess, are those, do they have gas envelope or are those only core?
They don't have gas envelopes. So this is exactly why we have these two very distinct diagonal lines here. This is really the cores without any atmosphere. So they have basically always the same, they follow the same track in this mass radius diagram. And once they become more massive, they stay on the same track. If you have a gaseous envelope in this plot, you would end up in the less denser regions of that plot. So this cloud of planets here, these are our super-Earths that also have a significant envelope.
Okay, thanks. The next one is a very interesting talk, Martin. We propose in our poster, this is from Nienka van der Marel, a scenario where super-Earth and Jupiters do not form in the same systems due to the capability of Jupiters to create pressure bumps, which limit radial drift. My question is, what is the occurrence of super-Earth plus Jupiter with respect to super-Earth without Jupiter?
Right, so it's more or less comparable, but only because we have these many warm Jupiters on intermediate orbits, and they would destroy the inner super-Earths quite often. So we have a large population of systems that after 5 gigayears, which we define as observation time, have only super-Earths, but no, only cold Jupiters, but no super-Earths. But this is due to dynamical interactions later on. So what we're actually seeing, what forms initially is both planet types usually form whenever the conditions are right. We need quite some mass reservoir for that. So as I said, maybe 100 Earth masses in solids. And keep in mind that we only have planetesimal accretion here. So normally there should be no direct connection between the inner and the outer disk in our simulations, only dynamical interactions, n-body interactions and such, but there's no pebble accretion involved. So we don't rely on an inward flux of solid material. That's actually interesting that our results are here are not, let's say, diluted by an additional effect of a pebble flux that gets cut off. It's really only the underlying properties of the disk and then dynamical interactions. And we're seeing that indeed these planet types seem to form together if there are not too many warm Jupiters involved.
Okay, great. Thanks a lot, Martin, again. And we have one more question, which we will be moved to Slack. So please go check that.
Thank you.
Okay, let's move on to the next speaker, Tim Hallett from McGill University. He will be talking about, can large-scale migration explain the giant planet occurrence rate?
Okay, can everyone hear me and see my slides clearly, hopefully?
Yep.
Okay, great. So in this project, we're interested in testing the large-scale migration paradigm against the giant planet occurrence rate, as well as against the mass distribution of low eccentricity giant planets. And we show that large-scale migration as a paradigm faces some real challenges in accounting for both of these observational artifacts. So this is an image from Pettigrew et al. 2018 from the California Kepler survey. They're plotting the occurrence rate, so dnd log p, the number of planets per log interval and orbital period, for different classes of planet. Cool colors are the small planets, so super Earths and sub-Neptunes. They have a flat occurrence rate beyond about 10 days in orbital period. You've already heard from Eve that this seems to be consistent with an in-situ formation scenario for these planets. But for giant planets below in warm colors, you can see their occurrence rate is of course not flat. The nd log p actually scales with period in this case. And as you've also heard from Eve previously, that this power law decrease in occurrence for giant planets seems to be suggestive of an origin through disk migration. Because in the standard, the basic type 1 migration scenario, the migration timescale, the time it takes for a planet to migrate from somewhere in the disk all the way into the disk inner edge, scales with the orbital period. So you expect more planets far out at large orbital period because the migration timescale is long. And you expect less planets as you move to smaller orbital periods, where the migration timescale becomes short. Planets can very efficiently shuttle into the disk inner edge. You can depopulate this region in the inner disk of planets naturally through migration. So that's why we're interested in testing it, because it's conceivable that it could be at work here, sculpting this occurrence rate for giant planets. Okay, so the first thing we do in the paper is we just flesh out a simple toy model of the giant planet occurrence rate in the migration paradigm. So we write dnd log p. In the migration paradigm, if we assume planets migrate in the type 1 regime, you can show, if you solve the equation of motion, that dnd log p at the end of the day scales with the migration time, which is expressing what I just explained. You expect more planets far out where the migration time is long, less planets as you move inwards when the migration time is short. This p to the 2/3, 1/2 plus beta minus gamma factor, that is expressing the fact that the migration time, of course, is sensitive to the disk structure. So we're assuming the disk surface density and temperature are power laws with power law indices beta and gamma, and the power laws in the orbital distance. So we're showing in the figure here that if you assume reasonable initial conditions for your disk, you can show that the dnd log p scales with period the same way the data does for reasonable initial conditions. So we were taking gamma to be 3/7, which is what you get if you assume a radiative equilibrium passive disk. Then you need beta to be basically what the minimum mass solar nebula is, or the minimum mass extrasolar nebula, so 1.5 or 1.6, in order to recover dnd log p scaling with period the same way the data does in the migration paradigm. So this is a 0th order indication that migration really could be at work here, and it warrants a bit further investigation here. So of course, migration doesn't happen on its own. There's other processes of happening, of course. So you're moving inwards, as indicated by the right, or the white arrow here. But of course, you're also accreting gas. So you have to start with a core, let's say 10 Earth masses. It needs to blow up into about 100 Earth masses to reach giant planet size. And the time scale for that is commensurate with the migration time scale for reasonable initial conditions of your planet and your disk. It's also true that as the planet is blowing up into giant planet sizes and migrating inwards through the disk, it's carving out a gap in the disk. So it's exciting waves in the disk, and the waves break, they dissipate, they deposit angular momentum. The torque from these waves is maximized at Lindblad resonances, and that introduces a repulsive Lindblad torque, which pushes disk gas away from the planet. So it's carving out a gap and depleting disk surface density in its immediate vicinity. And the upshot of that is migration speed slows down because migration depends on tidal interaction between the planet and gas in its vicinity. So as you're carving out a gap, you're slowing down migration. And we show in the figure here that to an order of magnitude, the timescale for accretion in blue and the timescale for migration in yellow and the timescale for gap opening in red are commensurate for reasonable initial conditions of your initial orbital radius. So we're taking, generally we find that warm Jupiters in our models are seeded from about a few AU, 1 to 5 AU roughly. And at that regime, these timescales are commensurate within roughly an order of magnitude. So what we're pointing out here is that you need to take this, you need to do a numerical approach here. You can't do an analytic approach and assume one process happens before the other. This is kind of, they're all kind of simultaneous for reasonable initial conditions. So that's all we're pointing out here. The first result I'm going to point out here is a very simple migration model. So in red, I'm plotting the occurrence rate of giant planets from Pettigrew et al. 2018 from the California Kepler survey for giant planets. So d log p scales with period the same way the data does. In blue, there's a very simple migration model. We're assuming planetary cores are sprinkled randomly in logarithmic period initially, because as Eve has already explained, that falls out naturally if you assume cores form through major mergers and giant impacts between themselves. We let them migrate through the disk. In the type 1 regime, we don't account for gap opening, hence the label here, no planetary gap. We don't account for gas accretion. Lo and behold, we get what we predicted analytically. d log p scales with period, so no surprises there. But of course, in the dark navy, we have to account for gap opening. That's an intrinsic property of migration in giant planets and disks. So we account for gap opening in the dark navy curve. The picture here is these planets are migrating inwards to smaller and smaller orbital periods. As they reach the inner disk, the disk becomes less puffy. It's less vertically extended due to hydrostatic equilibrium. This is kind of seen in our cartoon here. The disk becomes less puffy. It's easier for planets to carve out deep gaps to repel disk gas away from their orbits and slow migration down. So this preferential slowing down as planets open deeper and deeper gaps as they reach smaller and smaller orbital periods flattens the occurrence rate. It lengthens the migration time scale. This is a general result. It's not sensitive to how you set up your initial period distribution. You can show this analytically. And it's also, you could ask the question, well, can you tune your disk? Can you use power law indices such that you can recover a slope like the data in the deep gap limit? And the answer is no, not for physically reasonable values. So now we're kind of stuck. I mean, is this hopeless? Are we kind of just stuck with gap opening, throwing a wrench into things? And the answer is not quite. If you allow for an increasing outward mass gradient in your planet distribution, so small mass planets on the inside at small orbital periods and large mass planets on the outside at high orbital periods, you can counteract the effect of gap opening because the gap depletion factor, the amount by which you can deplete disk surface density near the planet by repelling disk gas away from itself, depends superlinearly on the planet mass. So small planets open small gaps. That's what we're showing on the cartoon here. So there's a modest torque involved with small planets. Large planets, on the other hand, can open deep gaps. They have a large torque, which repels disk gas away from their orbit. So this can counteract the effect of gap opening and flattening the occurrence rate. So you can get a slope that maybe in some cases can reflect the data and scale with period. So that's what you need. If you want migration to work, this seems to be what you need. A natural way to achieve this is with planetary atmospheres that have zero contributions from dust grains in the opacity. So maybe the dust grains have coagulated out and they don't contribute anymore to the opacity. The reason why you need this is because in the early regime of gas accretion on the planetary cores, the cooling limited regime, you have a proto-atmosphere, it's cooling off, it's contracting, it's freeing up more space inside the planet's Hill sphere or Bondi sphere for disk gas to replenish the atmosphere, and you can continually grow that way. The farther on the disk you are from the central star, where it's cold, which I've indicated in the cartoon here, low vibrational degrees of freedom can freeze out. Your opacity drops, you can reach runaway much faster. Cooling and therefore accretion happens much quicker. So you can reach larger planet masses on the outside. On the other hand, if you're close to the central star where the disk is hot, cooling takes longer, accretion takes longer, it takes longer to reach runaway, you can reach smaller masses. So this is a natural way to achieve an increasing outward mass gradient if you have opacities in your atmospheres that have no contribution from dust grains. We're showing in the figure here that if you use these stipulations, you can indeed recover the data within the error bars. This is the blue histogram here, but it still requires fine tuning. You have to fine tune exactly what initial conditions you're setting here. And we're pointing out this again. So if you set different core masses, if you set different disk masses, you will get different predictions from the large scale migration paradigm for the final distribution in period space of your giant planets. But of course, this is a simplified model. And in nature, core masses will have a variation, disk masses will have a variation, of course. So the next thing we do is extend our model here. So in the left column, we're sampling the disk masses log uniformly. We're not sampling core masses. We're keeping them constant at 15 Earth masses. In the top, you can see the occurrence rate in period space. You can get the occurrence rate within the error bars. Of course, this is again sensitive to exactly what core mass you choose, but if you're generous and you let it work, if you choose the right core mass, you can get it within the error bars. On the bottom, we're plotting the mass distribution, so the cumulative mass distribution against low eccentricity giant planets. In red colors are the hot Jupiters, in orange are the warm Jupiters, blue are the cool Jupiters. You can see the theoretical predictions in dash curves are bottom heavy. There's a large discrepancy between theory and observation in this case. Even if you account for observational biases against finding low mass objects, this is a large discrepancy, and it'd be helpful in the future when the day comes, we have a uniform, unbiased sample of warm Jupiter masses or maybe hot Jupiter masses. That would really help in pinning down predictions from the migration paradigm in this case. But of course, we have to sample disk masses, so we do that next in the right column. We choose a log normal distribution centered at 15 Earth masses. You can get the period distribution within the error bars once more. It's kind of marginal. You're kind of just inside the error bars. And again, it's sensitive. But you do better for the warm Jupiter mass distribution. The hot Jupiters are still bottom heavy. And even to get this sort of marginal agreement between the period distribution and the mass distribution, it's sensitive to exactly how you set things up. So if you have a width of your distribution of cores that's too wide, or you center the core mass distribution at 25 Earth masses or 10 or something like that, your predictions change pretty dramatically. You can go way outside of the error bars and the period distribution, for example, depending on exactly how you set this up. It's also true that in general, in every iteration of our models here, the hot Jupiter mass fraction is always bottom heavy, or the mass distribution is always bottom heavy. And the number fraction of warm to hot Jupiters is of order unity. So that's an order of magnitude lower than the observations that's of order 8 or 10. So migration in itself it doesn't seem to be able to reconcile even the number fraction of warm to hot Jupiters. So just the upshot of all this is that large scale migration as a paradigm, it faces real challenges. As I've already explained, it's very sensitive to initial conditions. You have to stipulate that you need an increasing outward mass gradient. You need distance-dependent opacities in your atmosphere. Even then, it requires fine-tuning. And then just to close here, it seems like not only us, but other groups in the past few years have kind of pointed against this large-scale migration idea, because there's a number of disk-planet interactions that have been pointed out in recent years that prohibit large-scale migration. They stop migration prematurely through a variety of disk-planet interactions. And at which point, if you're not migrating through large-scale migration through AU scales, maybe migration is not exactly what is setting the final distribution of planet periods and masses. Maybe it's something that resembles in situ, where migration might happen early, but through many possible disk-planet interactions, it might just halt prematurely and you're left with something resembling in situ formation. So yeah, that's all I have to say, and thanks for listening.
Okay, thank you, Tim. We have one question from Q&A. Have you compared your model to the period distribution of cold Jupiters at larger separations measured by radial velocity surveys?
Yeah, that's a good question. We haven't explicitly done that for a number of reasons. One is we have to really kind of build on our model here and calculate the viscous evolution of the disk and do a really kind of a more detailed, more fine-tuned study here. It's also true that we were interested in Petigura et al. 2018. It's very well characterized. At larger separations, I know there's a number of new papers coming out showing a bump in occurrence, for example, at a few AU, maybe near the ice line or something. That's a good topic for future work. It's really interesting to think about. But for the purposes of this exercise, no, we're not interested in that, and we haven't checked it explicitly.
Okay, thank you. I don't see any more questions. So if you have any more questions, please go ahead and post them on Slack, and let's move on to the next speaker. Thank you, Tim, again.
Thank you.
Okay, our next speaker is Nick Choksi from UC Berkeley, and Nick will be talking about sub-Neptune formation, the view from resonant planets.
Hi, everyone. Is my screen visible?
Yes, it is.
Okay, great. So I'd like to tell you a little bit about how we can use the sample of resonant Kepler planets to tell us something about planet formation. So Eve showed this plot in her review talk of the Kepler period ratio distribution. Some key takeaways are that most pairs of planets are not in resonance. But there are these excesses, these spikes in the period ratio distribution near the first order resonances. And so we like to understand what information is contained in these spikes. Ideally, we can use the height of the spike, just the overall frequency of resonant planets. But we could also use the precise location of the spike. These near resonant planets, they're distributed asymmetrically around the resonances. They prefer to be about 1% or so wide of resonance. So their period ratios are about 1% larger than a perfect integer ratio. And so I'll talk about where this characteristic 1% offset scale comes from. But I do want to highlight that the qualitative point that resonant systems like to be a little bit wide of a perfect commensurability in their period ratios, it actually turns out to be sort of a basic feature of these resonances, albeit one that's maybe not widely appreciated. So I have a few movies here to try and illustrate this point. In this first one, I have 2 planets. Period ratio is exactly 3:2. The outer one is on a circular orbit. The inner one is a test particle on an eccentric orbit. And I've started the 2 planets off along conjunction, so they're at their point of closest mutual approach. And that conjunction is at pericenter of the inner planet's orbit. And watch for where the next conjunction lands. I'll lay down a green X at every conjunction, and boom. And so you see with this configuration with a period ratio of exactly 3:2, that all of the conjunctions always land exactly at pericenter of the inner planet's orbit. And because everything's symmetric around peri, all of the angular momentum exchanges that the 2 planets give each other exactly cancel out before and after peri. And so the whole system is exactly repeatable and stable. This is a so-called resonant fixed point. In real life, though, the story gets more complicated because these 2 planets tug on each other and they induce precession in each other's orbits. And so I've folded in this precession term into this inner planet's orbit now, this test particle's orbit. The period ratio is still 3:2, but now you see that because peri is moving, conjunctions don't land exactly at peri anymore, right? They're sort of peppered all over the place. And so you've lost that stability, which is afforded to you by having your conjunctions at peri. So if you want to regain that stability, there's a very natural way to do it, right? It's just to change your period ratio a little bit, to adjust your timing so that you can land at peri again. And so that's what I've done in this last movie. So now the period ratio is not 3:2, it's 3:2 plus epsilon. And you see that even though peri is moving, the timing is just right so that conjunctions always land exactly on peri. And so you've regained that stability. So as long as you have a precession, and the precession in these resonances goes as 1 over the eccentricity, so as long as you have finite eccentricity, you'll have a precession, and your resonant equilibrium for these 2 planets is going to be, in general, is going to be a little bit offset from a perfect integer ratio. It has to be. The other thing I want to highlight is because the precession goes as 1 over e, if you want to wedge planets further apart, the way to do it is just to damp away this eccentricity so that you increase the precession rate. And of course, there's a very natural damper of eccentricities in the planet formation process, and that's just gas dynamical friction. At the same time, though, the story is a little more complicated because the disk damps away eccentricities, but it's also driving orbital migration. And so I have one more movie here to illustrate how this works as planets shuffle around in the disk due to orbital migration, they trap into resonances, and at the same time, their eccentricities are being damped away. So here I have 2 planets, initially not in resonance. The inner one is a test particle, the outer one is massive, and I'm going to send the outer planet, this outer planet inwards to mimic disk migration. And watch what happens when the 3:2 resonance runs into this inner test particle. You'll see that the test particle starts to migrate in lockstep to maintain the resonance, but now its eccentricity has been increased. And the eccentricity increases because of so-called resonant forcing of eccentricity, right? Resonances in the presence of orbital migration tend to jack up eccentricities. We see this all the time, for example, in the solar system. But this eccentricity, this forced eccentricity from the resonance, it has to compete. It has to compete with disk eccentricity damping by dynamical friction. And so you end up reaching an equilibrium eccentricity. That equilibrium eccentricity depends just on the ratio of the circularization timescale, the eccentricity damping time, and the orbital migration timescale, because it's orbital migration which is responsible for this resonant forcing up of eccentricity. Because you have an equilibrium eccentricity, you have an equilibrium value of that orbital precession, because the precession just scales as 1 over the eccentricity. And of course, it's the precession which is responsible for forcing your 2 planets to be a little bit wide of a perfect integer ratio. And so ultimately, this equilibrium eccentricity ends up corresponding to an equilibrium separation of your 2 planets, which is offset from a perfect integer ratio. And it's just dictated by the ratio of these 2 timescales, the migration and circularization times. So I'd also like to note that in the presence of eccentricity damping, these resonances can be unstable if the planet masses are low enough. So this instability, actually it's an overstability, was first discovered analytically by Goldrake and Schlichting. And in their original paper, they actually claimed that most of the sample of resonant Kepler planets, or sorry, most of the Kepler planets in general, were of low enough mass that, that they would be subject to this instability. So we looked into this again. It turns out that with more up-to-date planet masses, Twiddle 10M Earth, these are masses that we've gotten from RVs and TTVs, that with these more up-to-date planet masses, actually most of the Kepler sample is stable. And so once you're trapped in resonance, you're stuck there. There's no getting out. So it is a real instability. We can reproduce it. It's just not relevant for the Kepler planets. So that's sort of the physics at play. Now let me talk a bit about what we did to extract some information from the resonant features in the data. So we just did a little population synthesis experiment. So we mocked up a population of sub-Neptunes and super-Earths, just laid them down in disks, and then evolved them subject to these migration and circularization effects. And then the only free parameter in all of this is the disk surface density, right? It's the mass of the disk which controls the rate of migration and eccentricity damping. And so this is what we're going to fit to the resonant features in the data, just a single parameter fit. Now I do want to emphasize, we're not trying to model planet formation ab initio. We are using present day masses of these sub-Neptunes and super-Earths. And so when we fit this sigma to the data, you should really interpret it as a surface density of the disk around the time that these planets finished forming, around the time they finalize their masses, complete the final doubling in mass or so. We're just trying to get a handle on what the disk looked like when the planet formation was wrapping up. Were these super-Earths and sub-Neptunes born into very gas-rich environments in which the surface densities of gas to solids were very high, or just the opposite in gas-poor environments? So here it is. The black histograms are the observations. Different colors are different surface density models. Of course, at low surface densities, nothing happens. There's no disk to drive the show. At high surface densities, it's just the opposite, right? There's too much disk. The orbital migration timescales in these disks are so short that everyone gets shoved into resonance. This is a manifestation of the classic over-migration problem in disks with their full complements of gas. But as the gas disk dissipates, surface densities decrease. They decrease with time, right? And so what this data are really pointing us to is super-Earths and sub-Neptunes coming onto the scene. They don't even show up until the surface densities have decreased substantially. Our best fit surface densities for these resonant features in the data are 20 grams per square centimeter. They're orders of magnitude lower than a minimum mass nebula. So these are really gas poor environments that the data constrain us to be in. Gas poor, but not gas empty, right? We do need a little bit of gas to drive just a little bit of short scale orbital migration. There is migration going on here, but it's not a lot, right? You're just nudging planets into resonance. In particular, you're just nudging the ones that were already close to a resonance and nudging them over and into this resonant peak. Okay, so orbital migration does not have to be synonymous with wholesale migration throughout a disk, right? You can have the best of both worlds. You can form your super Earths and sub-Neptunes later in the disk lifetime when there's just not enough gas around to induce huge changes in orbital period and trap everyone into resonance. So everything I've shown you here was for the 3-2 resonance, which has the most data, the clearest resonant peak. But a way to test all of this is to take the best fit surface density for the 3-2 and then smack it on to the 2-1 resonance, right? Just as a total test of the model. And so it turns out that this does work. Modulo low signal to noise, at periods of greater than 15 days, we think things look pretty good. The story changes though, qualitatively at shorter period for the 2-1. These observed pairs near the 2-1 resonance, wide of the 2-1, they're further apart from one another by a factor of 2 or 3 than these model pairs. So we think qualitatively that this may make sense. At short period, stellar tidal interactions start to come into play. Tides can continue to damp eccentricities. That increases orbital precession rates. And then that forces planets further apart and wedges them rightwards in this space. So the story may hang together, at least qualitatively. The disk sets the baseline asymmetry over a few million years, and then tides continue to sculpt this distribution on gigayear timescales at short period. But I think there's more work to be done here to iron out these details. And I'll end there and take any questions. Thanks.
Thanks a lot, Nick. I really like the animation about the mean motion resonance and precession and eccentricity damping. It was very clear.
Thank you.
While we're waiting for questions, I just wanted to comment that when there's a gas disk, right, there's an additional factor where which can contribute to larger mean motion resonance ratio than what it would be. So, which is the spirals. So in gas disks, planets can generate spirals, and if you have 2 planets generating spirals, they can push each other's away. So if you think about 2-to-1 mean motion resonance, those spirals act in a way that the exact ratio is slightly larger than 2-to-1. Of course, the exact ratio is dependent upon how massive the gas disk is and the mass ratio between the planets, but usually 2.05, 2.1 to 1, 2.1 to 1. So yeah, that was just my comment. Are there any questions from audience? Okay, we have one question. Jack Leeser's talk mentioned uncertainties in orbital periods due to TTVs. Would this affect the period ratio pile up at all?
So I think that may be a question best directed to Jack, but I do know that in the original version of Jack's abstract, I think he ended up giving a slightly different talk than he had planned, but I remember reading the original version of his abstract, and in it he mentioned that in their reanalysis of the Kepler data, that this period ratio spike is robust. So I think it still holds up.
Okay, thank you.
And
we have
to add to that, we have theoretical reasons to expect there to be this resonance spike as well.
Okay, thank you. We have a couple more questions, but we are running out of time, so we will move on. So please check on Slack. Our last speaker of the session is Juliet Becker from Caltech, and she will be talking about the origins of multi-planet systems in misaligned nearby companions. Please go ahead, Juliet.
All right, well, hello everyone. So I'm happy to continue this section on the architectures of planetary systems. So I'm going to start with a plot that we've seen a couple different versions of already, which is the plot of discovered exoplanets, confirmed exoplanets actually so far. And in this plot, I have converted radii to masses. So every plot's on this chart, even if there's not actually a mass measured for it. What we've already learned from this plot is that there's a lot of distinct efforts that go into generating each of these populations of planets. And we spent Monday talking and Tuesday talking about how those populations are assembled, how we discover these planets. What we've been talking about today is kind of the covariances in planet occurrence. So when you have multiple types of planets on this diagram from different populations in the same system, what does that look like? How often do particular types of planets occur with other types of planets? So what I'm talking about today is one very particular covariance of systems. So first, I'm just going to summarize the populations of interest for me. So the first population of interest is the super Earth population, which was extremely well studied by Kepler and K2. And I guess TESS also continues to discover these planets. And the things that we've learned from mainly the Kepler mission include this plot that Lauren Weiss showed earlier today, showing the peas in the pod relationship, where planets within a system tend to have similar spacings and similar radii. We've also learned that this architecture of system, these tightly packed, close-in systems of multiple planets are actually pretty common. So more common than we would have expected prior to the transit discoveries that Kepler enabled. So this is the first population, and I call these STIPs, Systems of Tightly Packed Inner Planets, an acronym that's been kind of in and out of popularity the last few years. But this is the first population that I care about. They're pretty common. Next, let's return to that period mass diagram and take a look at a different, distinct, but somewhat overlapping population. So this is the ultra short period planets. So ultra short period planets, as their names imply, are those with orbital periods of less than a day. We've already heard a little bit about the efforts to characterize their compositions and exactly how irradiated they usually are. But today I'm going to talk about them just from a strictly dynamical standpoint. So another summarizing plot to show the distribution of ultra short period planets. Here is a plot from Wen et al. 2018 that shows all the multi-planet systems that contained ultra-short period planets at the time the paper was published. You'll see the ultra-short period planets in red. And unlike the STIPs, which are relatively common, so previously we said those occur around 20 to 30% of systems, ultra-short period planets are a lot more rare. So they occur in roughly 0.5% of systems. So obviously these two system types do have some overlap, because on this diagram we can see that ultra short period planets occur in STIPs pretty often. Now, there's one piece of information that if we return to this plot, we cannot see. And that piece of information is actually pretty important, and it's the direction of the angular momenta of these planets' orbits. So the direction of the angular momentum is defined by the orbital inclination, so the tilt of the orbit. And part of the reason why it's so hard to make a plot like this that uses true inclinations is that we, by definition, are only discovering a subset of planetary inclinations. So for both transits and radial velocities, we're going to have a much easier time discovering favorably aligned planets and favorably aligned multi-planet systems. Now, not to say that we can't discover systems with misalignments, which I'll tell you a little bit about one example of that in a moment. But what this does mean is that there is definitely a large selection effect in the planetary inclinations we can discover. With that in mind, there was this really interesting plot published by Fei Day in 2018 that showed for adjacent planet pairs and multi-planet systems, plotted by the ratio of the innermost planet's semi-major axis to the stellar radius, the difference in inclination of those two inner planets. So for the ultra short period planets, which are the ones with the shortest A to R star ratios, there's a large range of potential mutual inclinations that they have with their nearby companions. And that's not really surprising, because the closer a planet gets to its host star, the larger range of inclination it can have and still be discoverable. But the really interesting thing to look at is not really the absolute values of mutual inclination, but the fractional filling factor that the ultra short period planets versus the longer period planets fill of the allowable transiting region. So below this black line is all planets that actually would be seen to be transiting. And what you can probably notice without doing any statistical tests and just looking at the diagram is the fact that the shorter period planets fill a larger fraction of that region. So that's interesting because it kind of indicates there's something different dynamically going on in these two populations, ultra short period planets and longer period planets. Inclinations are not easy to get in transit though, because of this line, the fact that as you go to longer orbital periods, you can discover planets with only smaller inclinations. With that said, the test case that I'm going to be looking at today is the K2266 system. So this is the transit photometry from K2 that Joey Rodriguez and I published in the 2018 discovery paper of this system. A few things of note: there are 6 planet candidates. 4 of them are either validated or confirmed. These two, the 14 and 19-day planets, are maybe, possibly, probably in resonance. And then the innermost planet is an ultra short period planet on a grazing transit. So the grazing transit means that we could not see we could only see part of the planet passing in front of the host star. So here's a schematic showing the geometry of the system. So basically what the system looks like is the ultra short period planet, since it's only passing in front of the very edge of the star, it has a very high mutual inclination compared to the outer planets, which all are passing right near the midplane of the star. So the interesting thing here is, how do you create a system that looks like a stip? However, instead of all the planets being perfectly coplanar, the innermost planet is tilted relative to the outer ones. So there are 2 main ways that we found that this can happen. One of these is due to the dynamics of an exterior companion in the system. And the other one is due to dynamics involving the stellar obliquity and the stellar quadrupole moment. So I'm going to very, very briefly talk about the exterior companion because it's not my preferred solution to this problem. But one potential explanation for the geometry we see in this system is if there's an additional planet in the system that we didn't discover. Now that's totally feasible because, again, since these planets were discovered with transits, there is definitely a large range of parameter space in the system where we couldn't have seen planets. If you do inject an unseen companion into the system, then that can invoke some dynamics in the inner system that can cause the ultra short period planet to decouple from the outer system of tightly packed planets. Now, I'm not going to go deep into depth since I only have 12 minutes on how exactly we do this analysis, but here's the final result. Basically, what a final big set of numerical integrations showed us is that there is a regime where you can place a companion in the system that leads the ultra short period planet to decouple from the STIP, but the STIP planets to still remain well confined to a common orbital plane. So if you're interested more in this, feel free to ask questions in the Slack or check out our paper. But this is really not my preferred solution, so I don't want to spend a lot of time on it. Because if there were commonly these companions in systems, then we'd expect to see a lot more dispersion in STIPs in general. So most likely, although this is technically an explanation that physically works, my preferred explanation is our second option, which is dynamics arising due to the stellar obliquity and the stellar quadrupole moment. So we've already kind of heard about both of these things during this conference, but as a reminder, so stellar obliquity is just the tilt of the stellar spin axis with respect to the orbital angular momenta vectors. And then the stellar quadrupole moment is just a measure of the non-spherical component of the stellar potential. So if you have a rotating star, it kind of gets, like, you imagine orange that you're slightly smushing, you get a non-spherical term on the orange's potential, but also on the star's potential. So this term, the stellar quadrupole moment, can be parameterized as J2, and it's a lot stronger when stars are young and when they're rotating fast. So this is a diagram created with a combination of some analytic scaling laws and the data from Sean Matt's 2015 torque modeling for young stars. And it shows that for a star of K2266's mass, the J2 can span many orders of magnitude at early times and then decay as the star ages. So we'll get back to why this is important later, but the general trend I want you to take away from this plot is just the idea that the stellar quadrupole moment will decay with time, and the non-spherical term of the star's potential gets less important. Now we're moving on to another slide that I'm not going to spend a lot of time on. If you're interested, we can talk more. I can send you the paper. But since the K2266 system has such a short period inner planet, an ultra short period inner planet, it's really not feasible to do numerical integrations over billions of years. So instead, we construct a Hamiltonian model that has terms due to the potential of the disk, the potential of additional planets in the system, the potential of the stellar quadrupole moment itself, and then additionally a term of, describing the precession due to general relativity. So we can combine all these terms together, and what we get is a really easy to solve equation that allows us to not have to run numerical integrations, but instead just solve an analytical solution for what the evolution of the ultra short period planet's inclination will look like over time. Now, the dynamics of the ultra short period planets, they're kind of being pulled in two directions. So the two major modes driving the ultra short period dynamics are that due to the other planets, so the exterior planets in the STIP, but then also that due to the star. So the stellar dynamics is dominated by the quadrupole moment, although GR also plays a role. And then the other planets' perturbing potentials, as well as the disk potential, if a disk is present, will try to decouple the ultra short period planet from the host star. So now some quick animations. If we take that Hamiltonian and we solve it and then allow J2 to change, we can get the evolving phase space for the inclination longitude of ascending node of the ultra short period planet. So the red point corresponds to the fixed point, which evolves over time as we allow J2 to shrink and shrink. And if you don't have an early disk, this is a pretty smooth evolution. If you do have an early disk, then you get a little bit more violent evolution where the fixed point increases, decreases, increases again. And we'll turn these into plots that are a little easier to parse. So the reason for this is that in the case of no early disk, as the stellar J2 moment decays, the importance of the precession due to the quadrupole decreases and the importance of planet-planet interactions increases. In contrast, when you do have an early disk, in this early time, you have the disk and the stellar quadrupole fighting to dominate the dynamics of the ultra short period planet. Then the quadrupole decays then the disk decays and disappears, and then the planets start taking over as the quadrupole moment continues to disappear. Now, these plots that I've shown you today are just for one example configuration of a system. So you can imagine that you can have different initial conditions, different planet masses, different semi-major axis ratios, and all of those will affect which mode wins the dynamics. But the conclusion to take away from this is just the idea that to get misaligned multi-planet systems, where the ultra short period planet is misaligned with an outer plane of planets, it's actually a very natural consequence of stellar evolution. You just have to do a little bit of fine tuning to ensure that the STIP remains tightly packed in inclination so you can continue to discover it. But otherwise, it's actually a totally natural consequence of a process that we know happens. So with that, thank you so much for listening to my talk today, and I'd love to answer any questions.
Thank you very much, Juliet. We have a couple of minutes for questions. Okay, while I'm waiting, I was wondering if this is the only system where you see ultra short period hot Jupiter as well as STIP, or are there any other examples that we can learn more about it?
Yes, that's actually a good question. So actually, we don't know the exact radius of this planet because it was a grazing transit. We think it's probably around 2 Earth radii. But another good example of a system with this geometry is TOI 125. So TOI 125 is also a high multiplicity system that has a misaligned inner planet. That one, the inner planet is not as high signal to noise as in this system. So like, it's not guaranteed that it's actually real, but like, I'm pretty confident.
Awesome. it seems like your talk was super clear, so we don't get any questions yet.
I'll go with that. I'll go with that.
Okay, here we go. Oh yeah, a couple of questions. Juliet, great talk. Does the stellar quadruple moment mechanism for misaligning the USP from the STIPs predict that the equatorial plane of the STIPs differ from that of the star?
Yes, so it's a requirement that there is some misalignment between the stellar spin axis and the initial planet forming plane that the STIPs will inherit. And it seems like that's a pretty natural, to at least get a few degrees of initial obliquity misalignment is probably a pretty natural initial condition. But I would not be able to tell you exactly what the range of potential obliquities would be. It depends on the disk parameters.
Okay, great. We have 2 more questions, but I guess we will move that to Slack as we are already 4 minutes behind. As I said earlier, we have a poster pop. So if you can go ahead and play, Juliet.
Hi, my name is Mallory Harris, and I am a second-year graduate student at the University of New Mexico. A lot of the exoplanet community was really excited that the test mission prioritized M-dwarf targets because it would allow them to extensively study their habitable zone. For my work, though, I intend to use this sample to conduct a survey of the coldest planets orbiting low-mass stars. By looking into this region of parameter space that up till now has been somewhat underexplored, I will be able to constrain the occurrence rates of M-dwarf planets with periods greater than 20 days, while also providing targets for future mass and atmospheric characterization. The planets found over the course of the study could contribute to a number of questions about planet formation and evolution around low-mass stars, such as can gas giants form in these systems, and would the planets in their habitable zones have the necessary volatiles to host life? If you're interested in learning more about how this study is being conducted and the preliminary results, please check out my poster and send me your questions.
Okay, great. With that, let's thank all the speakers again. And let's come back at the top of hour, which is in 25 minutes.
Hey, Jesse.
Hey, Sarah.
I was curious. Yeah, hey. I'm just wondering if there are any announcements before we get started at the top of the hour.
Thanks for checking. No, just feel free to take it away.
Okay. And there's no poster pops at the end because we did it in the last one, right?
Exactly.
Okay. Okay. Sounds great. Thank you.
No worries. Thank you for sharing.
Yeah. Okay, hi everyone. It's the top of the hour, so we can go ahead and get started. Welcome to the second half of our session on the architectures of systems from a theoretical perspective. I'm Sarah Milholland from Princeton University, and I'll be chairing the session here. So we have a pretty short session of 3 15-minute talks. And as we've been doing, I encourage you to use the Q&A function as opposed to the chat for questions. And also please check out the posters that we have for this session. So our first talk today will be from Nader Hagegipur from University of Hawaii. So whenever you're ready, feel free to take it away.
Thanks so much. You hear me, right?
Yep, we can hear you.
Very good. You see my slides?
Yep.
Yeah, very good. Thank you so much. And it's great to give you this talk about the work that my student and I did last year to understand the effect that the migration of multiple giant planets could have on the formation of rocky planets. I'm showing this specific system, Khaleesi 876. I'm going to get back to this in a few slides, as this was basically the motivation behind the current work. Before I start talking about planet migration and what we have done and everything, I want to go back to the time before detection of the first extrasolar planet and say the following. We often hear that is said detection of extrasolar planets resulted into discovery of planet migration. Unfortunately or fortunately, that is not correct. Planet migration had been noted and worked out much before the detection of the first extrasolar planets. This is the seminal work by Doug Lin and John Papaloizo in 1986, where they work out the entire theory of planet formation. Soon after that, Bill Ward came out and presented a complement to this theory. I'm showing here a figure of that from that paper that shows how planets migrate and they open gaps. On the left side, you see the radial distance in terms of time, showing that protoplanets migrate. And so it is not of surprise that when 51 Peg was discovered in 1995, only a few months after that, Doug Lin put out a paper and explained the migration of 51 Peg B. If you read that paper, that Lin Papaloizo 1986 paper, and also Bill Ward's paper, the theory is extremely complicated. it would not have been possible to discover it, work it out, and write the paper only a few months after the first exosolar planet was discovered. This had been done much before that. The discovery of a solar planet that presented a lot of good questions. You're all familiar with that. This conference has been devoted to those. One of those came on at very early stages. This is Upsilon Andromeda system. This was the first multiple planet system discovered. As you see, it has giant planets and migrated to close-in orbits. And that raised the question, even at the early ages, that when giant planets migrate, what happens to rocky planets? Can rocky planets form? Can Earth-sized planets form? Can water be delivered to them? Can they be habitable? All those questions that we ask about our solar system were actually asked at that time as well. A bunch of good work was done on that topic. A series of papers by Fogg and Nelson in 2005 and 2007 came out, and they showed that through in-body integration that it is possible to migrate a giant planet and form rocky planets. Later on, Sean Raymond and Avi Mandel published a couple of papers show that if any of those planetesimals, protoplanets, are hydrated, there's a possibility of also delivering water and maybe even form planets as big as Earth in a habitable zone. So some simulations had been done on that. But along these lines, as the simulations were done and some of the questions were going to be addressed, some interesting things, interesting systems came about. In 1998, 1999, this system was discovered, Gliese 876, a 1.9 Jupiter mass planet at 60-day orbit. And a year after that, 2 years after that, there was a 0.6 Jupiter mass planet discovered at the 30-day orbit. And that immediately caught the attention of the community because this was the very first time two planets in a 2-to-1 resonance were discovered. So several of us who had worked on planet migration prior to detection of extrasolar planets had noticed that in our simulations that when we include dynamical friction, when we include some sort of dissipative force in our simulations, we see giant planets migrate and get captured into resonance, but they didn't really catch our eyes. Until this system was discovered, and then it was two nice papers by Lee and Peel and Zhu and Lin, who came out and explained how planet migration can actually get these planets into resonance, and that we need eccentricity damping, and when that applies, then what happens to the system? They all worked very good and nice. Now, the system didn't stop there. In 2006, a super Earth was discovered around this system. This was a planet, a 7.5 Earth mass planet in 2-day orbit that immediately raised the question that how that planet formed. I'll explain that in a second. And then later on in 2010, we discovered a fourth planet around the system. Now at the outer edge, we discovered a Uranus mass planets in 120-day orbits, and bring that to the slide that I put up at the beginning. Is a three-body resonance system. They are in Laplace resonance. There is a super Earth, and what is interesting is that the region interior to the innermost giant planets between super Earth is dynamically full, so that nothing else can be there. Now, whether the system holds another planet outside the outermost planet, we don't know, but what we know is that what we see here is dynamically full. Just as a point of reference, our solar system is dynamically full as well. So that and a few other systems like 55 Cangri, for instance, show similar behavior. Gliese 581 raised the question that how can we form these systems? In an article that I wrote for Annual Review in 2013, I put up these two figures. The article is about M stars. I'm sorry, it's about super Earth around M stars. So I put this figures, and I showed that it is possible to migrate planets and form hot Jupiters, form super Earth. Specifically, the one on the right shows what could have happened in GJ876. Two planets get captured into resonance. They continue, they scatter planets out, and one that happened to be in a closing orbit stays. That was all good, except that now the system had 3 planets, and there were many other systems with multiple giant planets that they had migrated, and that raised the question, what if we have multiple planets, and then we let those multiple giant planets migrate? How would that change this, this figure, and what would be the consequence of that? So the next 3 slides are the results of our work. Before I show them, I have to say 2 things. First, These results are unpublished, so I'm going to ask you to please respect that. And the second thing is that you may find some of the statements that I make intuitive. And that is exactly what I want to happen. I want you to see the physics that goes into illustrating what we think of and how that appears and turns into a planetary system. So let's do that. We carried out a few hundred simulations. We took giant planets, 1, 2, and 3 giant planets, and we considered planetesimal-driven migration. We took the disco planetesimals and planetary embryos with different masses. We considered different speeds for migration. We considered different masses for the giant planets. And here are the results. So this is a sample of 3 simulations for 1 planet migration. And what you see here is different type of configurations happens at different times. Keep in mind that I let the giant planet migrate all the way and crash into the star, right? However, what appears at different snapshots is a representative of what could be out there, meaning that in those systems out there, that evolution stopped where this snapshot happened. So let me explain that in more detail. Look at these, for instance, closing giant planets with multiple terrestrial planets, right? So this shows that depending on how fast or slow migration is, you will get some multiple planets. Some of them get captured into resonance, some of them don't get captured into resonance. This is something that we see out there as well. And depending on how fast or slow the migration is, the time for formation of this configuration varies. We also see closing giant planets with 1 terrestrial planet. And again, it depends how big the giant planet is, how fast it moves. We also see how Jupiter's depends on, so the planet migrates, it throws out everything, and then it stops. Now, the stopping mechanism is unknown, but what I want you to see is that it comes out of the physics. And there are cases where planet migrated, didn't stop, nothing, no planet was formed, and the whole thing crashed into the star, and nothing is left. We see similar trend in 2 planet migrations. Here, the second planet at the time t equals 0, the second planet is outside the frame, but it gradually comes in. But we see the same thing. We see that depending on the mass of the planets, whether they get captured into resonance, on the left panel they don't, on the right panel they do, depending on rate of migration, we see different architecture appearing. And with the 3 planets as well, and we see the similar thing happening, and sometimes all 3 planets crash into the star. Sometimes 2 of them get captured into resonance. That's the one on the left, and the other one is not in resonance. You get something similar to GJ76. Sometimes right above that, you get 3 giant planets with wide separations, but then with interior smaller planets going through. So this shows the different configurations, different architecture that comes out of it. And what I want you to take from this results is the following: that what we see is the final product, and it could have been due to the effect of the migrating giant planets with combined with planet formation, combined with rocky planet formation, and what is out there is one of these simulations, one of these results that happened, and at that time the system stopped. Or if it didn't stop, the giant planet crashed into the central star. And that basically sums up the type of architecture that comes out of this type of analysis, this type of simulations. This brings me to end of my talk. I gave this talk earlier this year in Houston, and I listed 12 different implications out of these results. I will post them on a Slack, but here, for the sake of time, I'm going to put only 4 of them up there. So systems with migrating giant planets can, in fact, form terrestrial planets as long as migration allows the giant planets to stop and not throw everything out. And that totally depends on the characteristic of the system. Water can be delivered to forming rocky planets in the exact same way as in our solar system through planetesimals and planetary embryos at the outer part of solar system asteroid belt in extrasolar planets in the vicinity of a snow line. It's not possible to determine the frequency of terrestrial planets simply because planet formation is stochastic. It is unpredictable and cannot be regulated. If I change mass of one of these giant planets by a small amount, the result will change. If I change the migration speed by a small centimeter per second, the result will change. However, you saw the pattern appearing, and that is exactly what we want. The goal of planet formation is not to reproduce a system exactly. It is to identify the region of the primary space and the type of physics that has the most significance to producing something similar to that system. And that's what we see here. And finally, hot Jupiters are rare because planet migration causes a large majority of them crash into the star. Thank you very much.
Thank you for that really nice talk. We have a couple of questions coming in. One question from Guy Smulders. What mass are the giant planets in your simulation? And are there a lower, is there a lower limit to the mass? So could migrating ice giants of Neptune mass have the same effect?
Very good. So the masses that we consider are Saturn mass and up. The Neptune mass, we expect from what we see from our simulations that the Neptune mass will have effect, but it's not going to be as strong as the larger planets. So as you migrate the Neptune mass closer, 2 or 3 Neptune mass as well, you will see more of the small rocky planets forming and staying around for longer times, and the time of formation lasts longer as opposed to larger planets. The larger the planet, the more effect it has with its migration and the most destructive effect it has with its migration.
Thanks. We have time, I guess, for one more question from Kevin Schloffman. So if hot Jupiters are rare because most of them migrate all the way into their host star, why does hot Jupiter occurrence increase so strongly with metallicity?
Kevin, jump planet formation is stochastic. I have no answer for that. I truly have no answer for that.
Okay, thanks so much, Nader. I guess we can go ahead and move to the next speaker now. So our next speaker of this session is Shannon Dulles from the University of Notre Dame. So whenever you're ready, looks like slides look good. And so take it away. Thanks.
Okay, great. Can you hear me okay?
Yep, we can hear you well.
Great. So yeah, my name is Shannon Dulles. I'm a grad student at Notre Dame, and I'm going to be talking today about a series of simulations that we are working on. Specifically, we are trying to quantify the improvement to planet yield of direct imaging missions. So this would be like WFIRST, which is now the Roman, and HableX and LUVOIR. And we're looking to see if a precursor ground-based RV survey beforehand would help choose targets for these direct imaging missions. So to do this, we're working on a series of simulations, starting with a planet population drawn from demographics. We have a realistic RV survey with telescope parameters. We then do MCMC orbital recovery to prioritize targets. And then we have detailed direct imaging yield calculations. What I'm mostly going to be talking about today is the first step in this process, which is how we constructed planet populations from demographics. I can only hit some of the highlights on this, but you should check out our recent paper here if you're interested. So to start off, we began with SAG-13 occurrence rates. Many of you are likely familiar with these. They were community-based meta-analysis of mostly Kepler and some additional published demographic occurrence rates. Since we're interested in direct imaging, we extend these all the way out to 30 AU. We are also looking at 2 additional demographic sets for comparison. So in the middle, we have replaced the Jovian occurrence rates with Fernandez et al. 2019. And we are also using for comparison Cumming et al. 2008 and in combination with Bryant et al. 2016. And since SAG-13 published optimistic and pessimistic versions for each of these, we have a total of 9 demographic sets for comparison with optimistic and pessimistic for each of these sets. So the main difference between these is the variation in the Jovian occurrence rates. So SAG-13, when it's extended and we've converted to mass from radius using Chen and Kipping, we see that it basically grows in semi-major axis, whereas Fernandez 2019 shows a turnover that's been discussed many times during this conference. Bryan and Cumming shows a break, basically, where we transition between them, likely due to selection effects. Some of you may have already spotted the problem, however, when we're just extending these occurrence rates out to 30 AU, because they're power laws, we get kind of insane amounts of planets in each system. So this naive extrapolation leads to unrealistic occurrence rates that could never be stable. So our solution is to use dynamical stability. Basically, we calculate dynamical stability based on mutual Hill radii that should indicate long-term gigagear stability. We check every planet in a system with every other planet, and in any conflicting unstable pairs, we keep the larger planet of the two. We also implement what we're calling a trusted region. So within about half an AU, if any of the planets we would predict get eliminated via stability checks, we redraw the system entirely. This is because we highly trust Kepler occurrence rates in close semi-major axes. Okay, so based on our stability assessments, we see a large impact in the occurrence rates that are able to be stable, particularly with the more optimistic occurrence input rates. We see that the stable lines, which are the solid lines down below, show much lower occurrence rates. We don't see much variation in terms of the input rate from the Jupiters. Mostly Neptunes are having a large impact on the occurrence rates. We also don't see much impact on the pessimistic rates, except at the largest semi-major axes. Here we can look at the percent difference between the input rates and the new stability assessed rates. We can see that most of the planets which are eliminated, which would be in deep purple, are the smallest and coldest planets. It's particularly noticeable in the optimistic rates. We're also interested in what planets are having an outsized impact on stability. So what we've basically found in comparing the kept planet versus the removed planet in unstable pairs is that the mass ratio of the unstable pair is pretty low. Most planets are eliminated by a planet that are slightly more massive than themselves. And they are also nearby in semi-major axis. The ratio here at the bottom right is generally close to 1. That being said, larger kept planets are able to have a greater impact on stability in other semi-major axes. not particularly surprising. We're also wondering if, since we removed so many of these unstable planets, if we're able to replace any of these planets via maximally packing the system. So are we able to add back in any planets that might be predicted? So to do this, we generate new sets of planets for each system, add in any that would be stable, and just keep repeating that for a number of iterations until essentially less than 1% of the stars would accommodate an additional planet. So with maximum packing, which we do only outside of the half AU trusted region, we basically see for the optimistic occurrence rates, we're not able to add in very many. You might recall that those were the ones that were most impacted by our stability assessment. We can add some at lower semi-major axes, but the original rates greatly exceed what we're even able to maximally pack at large semi-major axes. In the nominal case, they cross over at a few AU, but we are able to add a fair amount of planets close in. And with pessimistic rates, we're able to add in a lot more planets than the original rate. There's quite a bit of space in these demographics. So here we have the percent difference again. Basically, what we are seeing here is that we can add in planets here in the yellow and the green close to our boundary. It's a hard boundary at half an AU. But especially in the optimistic and somewhat in the nominal, we don't make up for those small Earths at large semi-major axes that were eliminated. Okay, so as an addition to SAG-13, we are proposing taking the cell-by-cell minimum of SAG-13 plus Fernandez with the nominally packed or the maximally packed occurrence rates. So this would be using SAG-13 for low semi-major axes where the systems are not maximally packed. And then once they get to unrealistic occurrence rates, we use just as many as can fit in the system. So in conclusions, stability can be used to extrapolate occurrence rates into unconstrained regions at large semi-major axes. This maximum packing that we are proposing can place an upper limit on cold planet occurrence rates. But since that does assume that these systems would be maximally packed at large semi-major axes, you could use stability checked without maximum packing, without replacing the planets, as a sort of nominal scenario, as opposed to an upper limit. In future, we're going to use these to quantify the improvement to a direct imaging space-based missions from a precursor RV survey. And I want to thank my co-authors on the paper as well. And thank you.
Thank you, Shannon, for your nice talk. So we have a question in the chat. You might have kind of addressed it a little bit towards the end, but so from David Bennett, have you tried using the wide planet distributions with semi-major axis from Fernandez 2019 or Wittenmeyer 20 in place of the stability requirements?
Yeah, so we use Fernandez 2019 for our Jovian occurrence rates in these. We still find that particularly the Neptunes, which are have very high occurrence rates in SAG-13, are unstable with the smaller mass planets. But yeah, certainly extending those out produces quite a bit of Neptunes. I don't know if that answered his question.
So if people have additional questions, can feel free to put them in the Q&A. But I guess I have one in the meantime. So I think maybe just 1 or 2 slides ago, you mentioned that you kind of do a transition from SAG-13 to Fernandez at some semi-major axis. And I was wondering how you, if I understood that correctly, like how you dictate where that transition goes.
So we put the transition at 0.225 Jovian masses. So that was a break in the power law, I believe, from Chen and Kipping, although I'd have to check exactly. And that was simply as like a comparison so that we transitioned at equal levels. Those are the like cutoffs for the various rates. Yeah.
Okay. All right. Do we have any additional questions? So we have another question in the chat from Lauren, probably Weiss, but Lauren W. So Shannon, great talk. Does the SAG-13 distribution extrapolated but with stability requirements resemble the Fernandez 2019 distribution? And if so, does this mean that the stability requirements might be an explanation for the peak in the giant planet occurrence around 3 AU?
Yeah, that's a great question. I think it highly depends on whether we're talking about SAG-13 nominal, optimistic, or pessimistic. So in pessimistic, it never gets up to maximally packed. So it looks just like SAG-13 in this case with Fernandez as the Jupiters. In nominal, we see that turnover out around, I think it's around 3 AU to 2 AU. But at optimistic, it's even lower. So yeah, that's a great point. I had not thought about it before, that could translate well. It's not exactly a point in the way that we've calculated it as the Fernandez paper predicts at 3 AU. It's more of a 2-dimensional space.
Great, thanks so much, Shannon. We have one more question, but I think we can take that one to the Slack for further discussion. So thanks again, Shannon. And we can move now to our last speaker of this session. This is Matthias He from Penn State. So whenever you're ready, you can take it away.
All right. Can you see my screen? Wait,
yep.
Click play. Now,
yep, it looks good.
Perfect. So hi, everyone. I'm a PhD student working with Eric Ford and Darren Ragazine, and I'll be talking about my work on inferring the intrinsic architectures of planetary systems using Kepler data. So in particular, I'll be focusing on the correlations of multi-planet systems and motivating a state-of-the-art model for planetary systems using AMD stability. So we heard Eric review and motivate the value of Ford modeling earlier in this week. So you've seen this diagram before, but I'm showing it again because it provides a nice high-level summary of our methodology, which is to Ford model the Kepler primate mission. So here I'll just highlight some of the key features of our procedure and then focus on the key results of our models. So we essentially develop or test several advanced statistical models that account for numerous correlations in multi-planet systems, which I'll explain throughout the rest of my talk. We then simulate physical catalogs by drawing planetary systems from our models assigned to Kepler target stars, including revised stellar properties from Gaia DR2 and also the Berger 2020 catalog, which we heard about previously. And as part of the system project led by my advisor, we have a very detailed model for the Kepler detection efficiency, building on the works of many people here. So crucially, this allows us to assess whether patterns in the Kepler population reveal something real about the true distribution of planetary systems, or whether they are caused by detection biases. And finally, we use various statistical methods to constrain our models by fitting to many of the marginal distributions of the Kepler data. So this includes things like the observed period, transit depth, and transit duration distributions, but more importantly, also the observed multiplicity distribution and statistics that probe multi-transiting systems, which I'll get into in the next few slides. Right, so in a paper we published last year, we showed with our 4 model that if we want to understand the detailed demographics of planetary systems, we really cannot treat planets as independent objects, but instead must account for the potential correlations in multi-planet systems. So for example, we find that Kepler multis exhibit correlated periods and sizes between planets in the same system, beyond simply just assuming that the only thing planets know about each other is being sort of adequately spaced for long-term stability. So we find that this is well described by a cluster model in which each planetary system has a number of planet clusters where the periods and sizes of planets in each cluster are drawn from a log normal distribution. And then the overall period and radius distributions follow single or broken power laws, at least in the range we considered, which is between 3 and 300 days. And so these results are driven by the distributions of pairwise period ratios and transit depth ratios for adjacent planets, which I'm showing here on the right, in addition to the multiplicity distribution on the top. So in each panel, the bold line is the model, the red lines are the model uncertainties, and then the gray shaded histograms or the X's in the top panel are showing the Kepler data. Right. Now, there are additional correlations in multi-planet systems, which have been hotly debated in recent studies and are commonly referred to as the P's inner pod patterns, as we heard from Lauren's talk earlier today. So these trends can be summarized into 3 questions, which are how similar in size are planets in the same system, how are they ordered in terms of their sizes, and how are they spaced? So to address these questions in greater detail, a paper by Gilbert and Fabricki earlier this year further tested our models and explored these trends by defining several complexity measures borrowed from information theory. So I'll use 3 of their metrics to briefly describe these patterns. So the first is a mass partitioning metric, which is basically a number between 0 and 1 that captures how equal the masses of planets in the same system are. So values close to 0 imply that the planets are equal in mass, while values close to 1 imply that one planet has most of the mass of the entire system. A related metric is the monotonicity, which again, captures the size ordering. So negative values here imply that smaller planets tend to be exterior to larger ones, while positive values imply the opposite. And finally, they also defined a gap complexity metric. Don't worry too much about the equation, but just know that you can compute it from a set of periods of the planets. And low values here mean that planets are very evenly spaced. All right, so what do these metrics imply for the Kepler systems? Well, Gilbert and Fabricki basically showed that planets in the same system tend to be very similar in size, as evidenced by having low mass partitioning. So here I am plotting the cumulative distribution of the partitioning metric for Kepler systems as the dashed line, and then the models, our models, as the solid line, except I've replaced mass with radius in the equation. So you can see our cluster models provide an extremely good fit here, which is perhaps expected given that we draw these cluster planet sizes. Now, in terms of the size ordering, we also find that systems tend to have positive monotonicity, which means that, again, they tend to be ordered and increasing size toward longer periods, consistent with many previous studies. So if you focus on the dashed line here, which is showing the Kepler data, you'll see that roughly 70% of the systems are above 0. But in our physical models, we have not included any size ordering patterns in the underlying systems. And if you take a close look, you'll see that our 4 model does produce a slight sort of positive preference for positive monotonicity in the observed systems. So the solid line sort of intersects at 0 monotonicity at a little less than 50%. So this implies that detection biases do play a role in producing a preference for the observed positive monotonicity, but it's not as strong as the effect seen in the data. So that indicates that there's some real underlying trend. And finally, planets tend to be very evenly spaced, as evidenced by having very low gap complexity. So the Kepler systems are significantly skewed to lower complexity values compared to our simulated systems. So even beyond our clustering in periods, there is additional uniform structure in the true distributions, true planetary systems observed by Kepler. So a key takeaway here is that since we're forward modeling all of these things, we are showing that these patterns are actually real and not just a result of detection biases. Now, you've also heard a lot about the Kepler dichotomy from Eric's talk and also Wei's talk. But just to very quickly review, this is the observation that the Kepler observed multiplicity distribution seems to indicate an excess of single transiting planet systems. So in our previous cluster models, we have actually allowed for two populations of mutual inclinations parameterized by separate Rayleigh distributions. So we found that while most systems have low mutual inclinations on the order of a few degrees, a significant fraction have high mutual inclinations, suggesting some sort of a Kepler dichotomy. These parameters are constrained not only by the observed multiplicity distribution, but also by the period normalized transit duration ratio distribution, which again, we heard about in previous talks. So the shape of this distribution is affected by the orbital eccentricities and mutual inclinations of the population as a whole. However, a sort of problem with this dichotomous model is that the high mutual inclination population is relatively unconstrained and likely produces many unstable systems. So this brings us to the AMD stability criteria, which is a condition in secular theory that predicts long-term stability by preventing overlapping orbits. So for a given system, you can actually compute the critical AMD and conveniently distribute that AMD amongst individual planets to ensure that the whole system is AMD stable. And so in our newest model, we still draw cluster periods and sizes, but then we calculate the critical AMD of each system and then distribute that AMD amongst the individual planets to set their eccentricity and mutual inclination components. And so this model actually produces a very similar fit to the observed population of planetary systems. So as you can see here, it also fits the observed multiplicities, P ratios, and transit depth ratios very well, amongst many other things. But it leads to some very different predictions for the underlying distributions. So in particular, it produces a single broad distribution of mutual inclinations and eccentricities, which is very different from the two Rayleigh distributions of mutual inclinations or the single Rayleigh of eccentricities, as was assumed in our previous models. Now, not only are the eccentricity and mutual inclination distributions marginalized over all systems different in this new model, but a key result is that they are correlated with the intrinsic multiplicity of the system. So you've seen this plot before in previous talks, but basically I'm plotting the median eccentricity and mutual inclinations as a function of the number of intrinsic planets in each system from our AMD model. And so this inverse relation between mutual inclination and multiplicity was first assumed in Zhu et al. 2018 as an explanation for the Kepler dichotomy, as we heard about in Wei's talk. And I plotted that here in the orange curve on the bottom for comparison. But it's interesting that we actually show how this can arise from the AMD stability limit and that we find a somewhat shallower slope. So I want to emphasize again that we actually did not assume a power law relation here or any parameterization in this model, but instead we simply distributed the critical AMD of each system, and the median values just happen to perfectly follow these power laws for both the eccentricities and the mutual inclinations. Now we also explored sort of what happens if we vary the overall level of dynamical excitation. So in other words, giving systems either less than or even more than the critical AMD. And we find that this trend with multiplicity remains. So these results are also relatively insensitive to our assumptions about the maximum, about every system sort of having the maximum AMD. The exact slope, however, does change slightly depending on the details of how we distribute the total AMD, whether equally per planet, as shown in green here, or per unit mass, as shown in purple. All right, so I have about a minute left before I conclude. I just want to say that I'm interested in exploring how our models can be used to predict the properties of additional planets in systems with already known planets, say from the test mission, to help inform radio velocity fallout observations. So as an example here, so we've seen sort of these multi-planet galleries from previous talks, especially Lauren's talk. But here, what we can do with our models actually plot these for all of those planets, including the non-transiting ones. And so here, as an example, I've plotted a sample of systems from our models conditioned on having a transiting super Earth around 5 days. You can see in each panel, you see those dots. So circles with red outlines denote non-transiting planets, and their colors denote the RV sum amplitudes. And here on the right, I plotted their RV time series for the total systems, as well as just the transiting planet in red. So you can see that oftentimes the transiting planet is actually not the dominant signal. And so by using our knowledge of the architectural properties of these planetary systems as a whole, we can make informed predictions about how many planets we should account for when modeling the RV time series, and maybe how many observations we might need to actually measure their masses. So I'm out of time, but I'll just leave up a summary of some key results, and I'll be happy to take questions. Thanks.
Thanks, Matthias, for your really nice talk. So we have a question coming in from Arthur Adams. So in comparing the cumulative distributions of planet occurrences, you had both, I think, Anderson-Darling and KS statistics to show they are drawn from a similar underlying distribution. So what is the difference between their values telling us about the way in which the distributions may differ?
Yeah, so right, that's right. We in our analyses, we actually use sort of multiple distance functions, mainly including terms of Anderson-Darling and KS, or Kolmogorov-Smirnov statistics. So these statistics, I guess, are different definitions about how similar distributions are. In particular, the KS statistic is just the maximum difference in the cumulative distribution. So I think that more strongly weights the sort of mode of the distributions, while the Anderson-Darling statistic is sort of an integral across the entire distribution. And so I think that more heavily weights the tails of the distribution.
So I had a question about, so since your forward model gets some constraints on the fraction of stars with Kepler planets, I'm curious how that compares between the AMD model and the 2 Rayleigh model, and also how it compares to some of the other values in the literature.
Yeah, that's a great question. So I have an extra slide here that kind of addresses it. So here I'm showing a bunch of different distributions from both the 2 Rayleigh model and the AMD model. And one thing we do find is that the fraction of stars of planets is quite sensitive to model assumptions. So namely, in the 2 Rayleigh model, we find that the overall fraction of stars of planets in this sort of 3 to 308 range is about 50%, and it rises, as you maybe saw in Eric's talk, it rises towards later spectral types. But in the AMD model, we actually find that the fraction of started planets is actually quite a lot higher, because sort of these each system has fewer planets due to the stability constraints. Is there another part to your question that maybe I forgot?
Oh yeah, that answered it. Thank you. Thanks so much. Yeah, so we've reached the end of this session. So thanks, Matthias, for your talk. And so poster pops were on the schedule, but as far as I'm aware, we've already gone through all of those. So are there any announcements from any of the organizers?
Sure. So thank you so much, Sarah, and to all the chairs and speakers today. We made today a bit of a shorter day. It's the middle of the week on a Zoom conference, so we're aware that everyone's going to get fatigued. Please go and spend the afternoon as far as you can, not thinking about Zoom and exoplanet demographics, and come back tomorrow 8 a.m. refreshed. We're going to talk about how exoplanet demographics vary as a function of the stars. So that'll be really exciting. In the meantime, please go check out the posters in the Slack. Check out today's e-zine from our amazing writers and artists who've contributed, and register for tomorrow night's science fiction panel. All right. Thanks so much, everyone. Have a good afternoon.
Hi, Helen. Can you hear me? Oh, I cannot hear you.
Sorry, I was muted.
Okay, good. Okay, thank you very much. Let me try to show my slides. Okay. Okay. So, hi. I can see now.
Yes.
The background is okay.
Mm-hmm.
Okay. Can you see my slides?
Not quite yet.
Oh yeah, because I need to share the screen. Yeah,
yes.
That's right.
Yep. You should be able to do that.
After I share the screen, can you see it now?
Yes, it looks good.
Okay, perfect. And I can move forward. Okay, and you can see me, I can see you, and you will have the green timing, right?
Yes.
Okay. Okay, sounds good.
Did you want, Ilaria, did you want to practice pinning Ellen so the timing stays there?
Oh, that's a good idea. Yeah. Okay, so let's see if I can do it. Pin video. Okay.
Yeah. And
now
then
I can
she won't
see
disappear.
Yeah. Okay, great. Thank you very much. Then
no worries.
we can we see each other tomorrow.
Okay.
Yeah, good to see you, Ilaria. Bye.
Yeah, bye. Nice to see you. Bye.